Learning objectives. In this chapter, the user will learn the following in detail: two-dimensional geometric transformations, clipping, point clipping, line clipping, polygon clipping, text clipping, logical classification of input devices, different input modes, interactive picture construction techniques, three-dimensional geometric transformations. Clipping. Clipping is a graphics package allows the user to specify which part of a defined picture is to be displayed and where that part is to be placed on the display device. Any convenient Cartesian coordinate system, referred to as the world coordinate reference frame, can be used to define the picture. For a two-dimensional picture, a view is selected by specifying a sub-area of the total picture area. A user can select a single area for display, or several areas could be selected for simultaneous display or for an animated panning sequence across a scene. The picture parts with the selected areas are then mapped onto the specified areas of the device coordinates. When multiple view areas are selected, these areas can be placed in a separate display locations, or some areas could be inserted into other larger display areas. Transformations from world to device coordinates involve translation, rotation, and scaling operations, as well as procedures for deleting those parts of the picture that are outside the limits of the selected display area. The viewing pipeline. A world coordinate area selected for display is called a window. An area on a display device to which a window is mapped is called a viewport. The window defines what is to be viewed. The viewport defines where it is to be displayed. Often, windows and viewports are rectangles in a standard position with the rectangle edges parallel to the coordinate axis. Other window or viewport geometries, such as general polygon shapes and circles, are used in some applications, but these shapes take longer to process. In general, the mapping of a part of a world coordinate scene to device coordinates is referred to as a viewing transformation. Sometimes the two-dimensional viewing transformation is simply referred to as a window to viewport transformation or the windowing transformation. But in general, viewing involves more than just the transformation from the window to the viewport. This figure illustrates the mapping of a picture section that falls within a rectangular window onto a designated rectangular viewport. A viewing transformation using standard rectangles for the window and viewport. In computer graphics terminology, the term window originally referred to an area of a picture that is selected for viewing, as defined at the beginning of this section. Unfortunately, the same term is now used in window manager systems to refer to any rectangular screen area that can be moved about, resized, and made active or inactive. In this chapter, we will only use the term window to refer to an area of the world coordinate scene that has been selected for display. Some graphics packages that provide window and viewport operations allow only standard rectangles, but a more general approach is to allow the rectangular window to have any orientation. In this case, we carry out the viewing transformation in several steps as indicated in this figure. The two-dimensional viewing transformation pipeline is shown in this figure. Next, to obtain a particular orientation for the window, we can set up a two-dimensional viewing coordinate system in the world coordinate plane and define a window in the viewing coordinate system. The viewing coordinate reference frame is used to provide a method for setting up arbitrary orientations for rectangular windows. Once a viewing reference frame is established, we can transform the descriptions in a world coordinates to viewing coordinates. We then define a viewpoint in normalized coordinates in the range from 0 to 1 and map the viewing coordinate description of the scene to normalized coordinates. At the final step, all parts of the picture that lie outside the viewport are clipped and the contents of the viewport are transferred to device coordinates. This figure illustrates a rotated viewing coordinate reference frame and the mapping to normalized coordinates. Setting up a rotated world window in viewing coordinates and the corresponding normalized coordinate viewport. By changing the position of the viewport, we can view objects at different positions on the display area of an output device. Also, by varying the size of viewports, we can change the size and proportions of displayed objects. We achieve zooming effects by successively mapping different size windows on a fixed size viewport. As the windows are made smaller, we zoom in on some part of a scene to view details that are not shown with larger windows. Similarly, more overview is obtained by zooming out from a section of a scene with successively larger windows. Panning effects are produced by moving a fixed size window across the various objects in a scene. Viewports are typically defined within the unit square normalized coordinates. This provides a means for separating the viewing and other transformations from specific output device requirements, so that the graphics package is largely device independent. Once the scene has been transferred to normalized coordinates, the unit square is simply mapped to the display area for the particular output device in use at that time. Different output devices can be used by providing the appropriate device drivers. When all coordinate transformations are completed, viewport clipping can be performed in normalized coordinates or in device coordinates. This allows us to reduce computations by concatenating the various transformation matrices. Clipping procedures are of fundamental importance in computer graphics. They are used not only in viewing transformations but also in window manager systems, in drawing packages to eliminate parts of a picture inside or outside of a designated screen area, and in many other applications. Viewing coordinate reference frame. This coordinate system provides a reference frame for specifying the world coordinate window. First, a viewing coordinate origin is selected at some world position P0 equals x0, y0. Then we need to establish the orientation or rotation of this reference frame. One way to do this is to specify a world vector v that defines the viewing yv direction. Vector v is called the view up vector. Given v, we can calculate the components of the unit vectors v equals vx, vy and u equals ux, uy for the viewing yv and xv axis, respectively. These unit vectors are used to form the first and second rows of the rotation matrix R that aligns the viewing xv, yv axis with the world xw, yw axis. We obtain the matrix for converting world coordinate position to viewing coordinates as a two-step composite transformation. Translate the viewing origin to the world origin. Rotate to align the two coordinate reference frames. The composite two-dimensional transformation to convert world coordinates to viewing coordinates is mwc.vc equals r and t, where t is the translation matrix that takes the viewing origin point P0 to the world origin, and R is the rotation matrix that aligns the axes of the two reference frames. This figure illustrates the steps in this coordinate transformation. This figure shows a viewing coordinate frame that is moved into coincidence with the world frame in two steps. A. Translate the viewing origin to the world origin, and then B. Rotate to align the axes of the two systems. Window to viewport coordinate transformation. Once object descriptions have been transferred to the viewing reference frame, we can choose the window extents in viewing coordinates and select the viewport limits in normalized coordinates. Object descriptions are then transferred to normalized device coordinates. We do this using a transformation that maintains same relative placement of objects in normalized space as they had in viewing coordinates. If a coordinate position is at the center of the viewing window, for instance, it will be displayed at the center of the viewport. This figure illustrates the window to viewport mapping. In this figure, a point at position xw, yw in a designated window is mapped to viewport coordinates xv, yv, so that the relative positions in these two areas are the same. A point at position xw, yw in the window is mapped onto position xv, yv in the associated viewport. To maintain the same relative placement in the viewport as in the window, we require that the following expressions be solved. Solving these expressions for the viewport position xv, yv, we have xv equals xv min plus xw minus xw min into sx. Likewise, yv equals yv min plus yw minus yw min into sy, where the scaling factors are Sx equals xv max minus xv min over xw max minus xw min. Sy equals YVmax minus YVmin over YWmax minus YWmin. Set of transformations that converts the window area into the viewport area. This conversion is performed with the following sequence of transformations. 1. Perform a scaling transformation using the fixed point positions of XWmin, YWmin that scales the window area to the size of the viewport. 2. Translate the scaled window area to the position of the viewport. Relative proportions of objects are maintained if the scaling factors are the same, Sx equals Sy. Otherwise, world objects will be stretched or contracted in either the x or the y direction when displayed on the output device. Character strings can be handled in two ways when they are mapped to a viewport. The simplest mapping maintains a constant character size even though the viewport area may be enlarged or reduced relative to the window. This method would be employed when text is formed with standard character fonts that cannot be changed. In systems that allow for changes in character size, string definitions can be windowed, the same as other primitives. For characters formed with line segments, the mapping to the viewport can be carried out as a sequence of line transformations. From normalized coordinates, object descriptions are mapped to the various display devices. Any number of output devices can be opened in a particular application, and another window-to-viewport transformation can be performed for each open output device. This mapping, called the workstation transformation, is accomplished by selecting a window area in normalized space and a viewport area in the coordinates of the display device. With the workstation transformation, we gain some additional control over the positioning of parts of a scene on individual output devices. As illustrated in this figure, we can use workstation transformations to partition a view so that different parts of normalized space can be displayed on different output devices. Figure shows mapping selected parts of a scene in normalized coordinates to different video monitors with workstation transformations. Two-dimensional viewing functions. We define a viewing reference system in a fixed application program with the following function. Evaluate view orientation matrix x0, y0, xv, yv, error, view matrix, where parameters x0 and y0 are the coordinates of the viewing origin and parameters xv and yv are the world coordinate positions for the view up vector. An integer error code is generated if the input parameters are in error. Otherwise, the view matrix for the world to viewing transformation is calculated. Any number of viewing transformation matrices can be defined in an application. To set up the elements of a window to viewport mapping matrix, we invoke the following function. Here, the window limits in viewing coordinates are chosen with parameters xwmin, xwmax, ywmin, ywmax, and the viewport limits are set with the normalized coordinate positions xvmin, xvmax, yvmin, and yvmax. As with the viewing transformation matrix, we can construct several window viewport pairs and use them for projecting various parts of the scene to different areas of the unit square. Next, we can store combinations of viewing and window viewport mappings for various workstations in a viewing table with the code shown here, where parameter ws designates the output device workstation and parameter view index sets an integer identifier for this particular window viewport pair. The matrices view matrix and view mapping matrix can be concatenated and referenced by the view index. Additional clipping limits can also be specified here, but they are usually set to coincide with the viewport boundaries. And parameter clip xy is assigned either the value noClip or the value clip. This allows us to turn off clipping if we want to view the parts of the scene outside the viewport. We can also select noClip to speed up processing when we know that all of the scene is included within the viewport limits. The function setViewIndex selects a particular set of options from the viewing table. This view index selection is then applied to subsequently specified output primitives and associated attributes and generates a display on each of the active workstations. At the find stage, we apply a workstation transformation by selecting a workstation window viewport pair, as shown below. where parameter WS gives the workstation number. Window coordinate extents are specified in the range from 0 to 1, normalized space, and viewport limits are in integer device coordinates. If a workstation viewport is not specified, the unit square of the normalized reference frame is mapped onto the largest square area possible on an output device. The coordinate origin of normalized space is mapped to the origin of device coordinates, and the aspect ratio is retained by transforming the unit square onto a square area on the output device. Clipping operations. Any procedure that identifies those portions of a picture that are either inside or outside of a specified region or space is referred to as a clipping algorithm, or simply clipping. This region against which an object is to be clipped is called a clip window. Applications of clipping include extracting part of the defined scene for viewing, identifying visible surfaces in the three-dimensional views, anti-aliasing line segments or object boundaries, creating objects using solid modeling procedures, displaying a multi-window environment, and drawing and painting operations that allow parts of a picture to be selected for copying, moving, erasing, or duplicating. Depending on the application, the clip window can be a general polygon or it can even have curved boundaries. We first consider clipping methods using rectangular clip regions, then we discuss methods for other clip regions shapes. For the viewing transformation, we want to display only those picture parts that are within the window area, assuming that the clipping flags have not been set to no clip. Everything outside the window is discarded. Clipping algorithms can be applied in world coordinates so that only the contents of the window interior are mapped to device coordinates. Alternatively, the complete world coordinate picture can be mapped first to device coordinates or normalized device coordinates, then clipped against the viewport boundaries. World coordinate clipping removes those primitives outside the window from further consideration, thus eliminating the processing necessary to transform those primitives to device space. Viewport clipping, on the other hand, can reduce calculations by allowing concatenation of viewing and geometric transformation matrices. But viewport clipping does require that the transformation to device coordinates be performed for all objects, including those outside the window area. On raster systems, clipping algorithms are often combined with scan conversion. Algorithms for clipping: point clipping, line clipping, straight line segments, area clipping, polygons, curve clipping, text clipping. Line and polygon clipping routines are standard components of graphics packages, but many packages accommodate curved objects, particularly spline curves and conics, such as circles and ellipses. Another way to handle curved objects is to approximate them with straight line segments and apply the line or polygon clipping procedure. Point clipping. Assuming that the clip window is a rectangle in standard position, we save a point P equals x, y for display if the following inequalities are satisfied. xw_min is less than or equal to x, which is less than or equal to xw_max, and y lies between yw_min and yw_max, where the edges of the clip window xw_min, xw_max, yw_min, yw_max can be either the world coordinate window boundaries or viewport boundaries. If any one of these four inequalities is not satisfied, the point is clipped, not saved, for display. Although point clipping is applied less often than the line or polygon clipping, some applications may require a point clipping procedure. For example, point clipping can be applied to scenes involving explosions or sea foam that are modeled with particles, points, distributed in some region of the scene. Line clipping. The following figure illustrates possible relationships between line positions and a standard rectangular clipping region. A line clipping procedure involves several parts. First, we can test a given line segment to determine whether it lies completely inside the clipping window. If it does not, we try to determine whether it lies completely outside the window. Finally, if we cannot identify a line as completely inside or completely outside, we must perform intersection calculations with one or more clipping boundaries. We process lines through the inside-outside test by checking the line endpoints. A line with both endpoints inside all clipping boundaries, such as the line from P1 to P2, is saved. A line with both endpoints outside any one of the clip boundaries, line P3, P4 in the previous figure, is outside the window. All of the lines cross one or more clipping boundaries and may require calculation of multiple intersection points. To minimize calculations, we try to devise clipping algorithms that can efficiently identify outside lines and reduce intersection calculations. For a line segment with endpoints x1, y1 and x2, y2, and one or both endpoints outside the clipping rectangle, the parametric representation x equals x1 plus u into x2 minus x1 and y equals y1 plus u into y2 minus y1, with lying between 0, u and 1, could be used to determine values of parameter u for intersections with the clipping boundary coordinates. If the value of u for an intersection with rectangular boundary edge is outside the range 0 to 1, the line does not enter the interior of the window at that boundary. If the value of u is within the range from 0 to 1, the line segment does indeed cross into the clipping area. This method can be applied to each clipping boundary edge in turn to determine whether any part of the line segment is to be displayed. Line segments that are parallel to window edges can be handled as special cases. Clipping line segments with these parametric tests require a good deal of computation, and faster approaches to clipping are possible. Some line clipping algorithms are Cohen-Sutherland line clipping, Liang-Boskie line clipping. This is one of the oldest and most popular line clipping procedures. Generally, the method speeds up the processing of line segments by performing initial tests that reduce the number of intersections that must be calculated. Every line endpoint in a picture is assigned a 4-digit binary code called a region code that identifies the location of the point relative to the boundaries of the clipping rectangle. Regions are set up in reference to the boundaries as shown in this figure. Binary region codes assigned to line endpoints according to the relative position with respect to the clipping rectangle. Each bit position in the region code is used to indicate one of the 4 relative coordinate positions of the point with respect to the clip window, to the left, right, top, or bottom. By numbering the bit positions in the region code as 1 through 4 from right to left, the coordinate regions can be correlated with the bit positions as bit 1 left, bit 2 right, bit 3 below, bit 4 above. A value of 1 in any bit position indicates that the point is in that relative position. Otherwise, the bit position is set to 0. If a point is within the clipping rectangle, the region code is 0, 0, 0, 0. A point that is below and to the left of the rectangle has a region code of 0, 1, 0, 1. Bit values in the region code are determined by comparing endpoint coordinate values x, y to the clip boundaries. Bit 1 is set to 1 if x is less than xw min. The other 3 bit values can be determined using similar comparisons. For languages in which bit manipulation is possible, region code bit values can be determined with the following 2 steps. 1. Calculate differences between endpoint coordinates and clipping boundaries. 2. Use the resultant sign bit of each difference calculation to set the corresponding value in the region code. Bit 1 is in the sign bit of x minus xw min, but bit 2 is in the sign bit of xw max minus x. Bit 3 is in the sign bit of y minus yw min, and bit 4 is in the sign bit of yw max minus y. Once we have established region codes for all line endpoints, we can quickly determine which lines are completely inside the clip window and which are clearly outside. Any lines that are completely contained within the window boundaries have a region code of 0, 0, 0, 0 for both endpoints, and we trivially accept these lines. Any lines that have a 1 in the same bit position in the region codes for each endpoint are completely outside the clipping rectangle, and we trivially reject these lines. We would discard the lines that has a region code of 1001 for one endpoint and a code of 0101 for the other endpoint. Both endpoints of this line are left of the clipping rectangle, as indicated by the 1 in the first bit position of each region code. A method can be used to test lines for total clipping is to perform the logical and operation with both region codes. If the result is not 0000, the line is completely outside the clipping region. Lines that cannot be identified as completely inside or completely outside a clip window by these tests are checked for intersection with the window boundaries. As shown in this figure, such lines may or may not cross the window interior. This figure shows that lines extending from one coordinate region to another may pass through the clip window, or they may intersect clipping boundaries without entering the window. We begin the clipping process for a line by comparing an outside endpoint to a clipping boundary to determine how much of the line can be discarded. Then the remaining part of the line is checked against the other boundaries, and we continue until either the line is totally discarded or a section is found inside the window. Set up our algorithm to check endpoints against clipping boundaries in the order left, right, bottom, top. To illustrate the specific steps in clipping lines against rectangular boundaries using the Sutherland algorithm is shown in the given figure. Starting with the bottom end point of the line from P1 to P2, we check P1 against the left, right, and bottom boundaries in turn and find that this point is below the clipping rectangle. We then find the intersection point P1' with the bottom boundary and discard the line section from P1 to P1'. The line has now been reduced to the section P1' to P2. Since P2 is outside the clip window, we check this endpoint against the boundaries and find that it is to the left of the window. Intersection point P2' is calculated, but this point is above the window. So the final intersection calculation yields P2 double dash, and the line from P1' to P2 double dash is saved. This completes processing for this line, so we save this part and go on to the next line. Point P3 in the next line is to the left of the clipping rectangle, so we determine the intersection P3' and eliminate the line section from P3 to P3'. By checking region codes for the line section from P3' to P4, we find that the remainder of the line is below the clip window and can be discarded also. Intersection points with the clipping boundary can be calculated using the slope-intercept form of the line equation. For a line with endpoint coordinates x1, y1 and x2, y2, the y-coordinates of the intersection point with the vertical boundary can be obtained with the calculation y equals y1 plus m into x minus x1, where the x value is set either to xw min or to xw max, and the slope of the line is calculated as m equals y2 minus y1 over x2 minus x1. Similarly, if we are looking for the intersection with the horizontal boundary, the x-coordinate can be calculated as x equals x1 plus y minus y1 over m, with y set either to yw min or yw max. The following procedure demonstrates the Sutherland line clipping algorithm. Codes for each endpoint are stored as bytes and processed using bit manipulations. Boskie line clipping. Faster line clippers have been developed that are based on analysis of the parametric equation of a line segment, which we can write in the form x equals x1 plus u delta x, y equals y1 plus u delta y, where u lies between 0 and 1, where delta x equals x2 minus x1 and delta y equals y2 minus y1. Later, Liang and Boskie independently devised an even faster parametric line clipping algorithm. Following the Liang-Boskie approach, we first write the point clipping conditions in parametric form, as shown below. Each of these four inequalities can be expressed as u pk less than or equal to qk, where k equals 1, 2, 3, and 4, where parameters p and q are defined as shown here. Any line that is parallel to one of the clipping boundaries has pk equals 0 for the value of k corresponding to the boundary k equals 1, 2, 3, and 4 correspond to the left, right, bottom, and top boundaries respectively. If for that value of k we also find qk is less than 0, then the line is completely outside the boundary and can be eliminated from further consideration. If qk is greater or equal to 0, the line is inside the parallel clipping boundary. When pk is less than 0, the infinite extension of the line proceeds from the outside to the inside of the infinite extension of this particular clipping boundary. If pk is greater than 0, the line proceeds from inside to the outside. For a non-zero value of pk, we can calculate the value of u that corresponds to the point where the infinitely extended line intersects the extension of boundary k as u equals qk by pk. For each line, we can calculate values for parameters u1 and u2 that define that part of the line that lies within the clip rectangle. The value of u1 is determined by looking at the rectangle edges for which the line proceeds from the outside to the inside. P is less than 0. For these edges, we calculate rk equals qk by pk. The value of u1 is taken as the largest of the set consisting of 0 and the various values of r. Conversely, the value of u2 is determined by examining the boundaries for which the line proceeds from inside to outside. P is greater than 0. A value of rk is calculated for each of these boundaries, and the value of u2 is the minimum of the set consisting of 1 and the calculated r values. If u1 is greater than u2, the line is completely outside the clip window and it can be rejected. Otherwise, the endpoints of the clipped line are calculated from the two values of the parameter u. This algorithm is presented in the following procedure. Line intersection parameters are initialized to the values of u1 equals 0 and u2 equals 1. For each clipping boundary, the appropriate values for p and q are calculated and used by the function clipTest to determine whether the line can be rejected or whether the intersection parameters are to be adjusted. When p is less than 0, the parameter r is used to update u1. When p is greater than 0, parameter r is used to update u2. If updating u1 or u2 results in u1 being greater than u2, we reject the line. Otherwise, we update the appropriate u parameter only if the new value results in a shortening of the line. When p equals 0 and q is less than 0, we can discard the line since it's parallel to and outside of this boundary. If the line has not been rejected, after all four values of p and q have been tested, the endpoints of the clipped line are determined from values u1 and u2. The pseudocode for Liang-Boskie algorithm is presented below. In general, the Liang-Boskie algorithm is more efficient than the Cohen-Sutherland algorithm since intersection calculations are reduced. Each update of parameters u1 and u2 requires only one division. and window intersections of the line are computed only once when the final values of u1 and u2 have been computed. In contrast, the Cohen-Sutherland algorithm can repeatedly calculate intersections along a line path even though the line may be completely outside the clip window. And each intersection calculation requires both a division and a multiplication. Both the Cohen-Sutherland and the Liang-Boskie algorithms can be extended to three-dimensional clipping. Solved example. Problem: use the Liang-Boskie algorithm to clip the lines in this figure. Solution: for line AB we have the following parameters. Since P2 equals 0 and Q2 is less than -2, AB is completely outside the right boundary. For line CD, we have the following parameters. Thus, U1 equals max of 0, minus 5 by 3 equals 0, and U2 equals minimum of 1 and 1 by 3 equals 1 by 3. Since U1 is less than U2, the two endpoints of the clipped line are 3, 7 and 3, 7 plus 3 into 1 by 3 equaling 3.8. For line EF, we have the following parameters. Thus, U1 equals max of 0, minus 1 by 6, minus 1 equaling 0, and U2 equals minimum of 1, 7 by 6, 5 equaling 1. Since U1 is 0 and U2 equals 1, the line EF is completely inside the clipping window. For line GH, we have the following parameters. Thus, U1 equals max of 0, minus 5 by 2, minus 4 by 3 equals 0, and U2 equals minimum of 1, 3 by 2, 2 by 3 equaling 2 by 3. Since U1 is less than U2, the two endpoints of the clipped line are 6, 6 and 6 plus 2 into 2 by 3 plus 6 plus 3 into 2 by 3 equaling 7 into 1 by 3, 8. For line IJ, we have the following parameters. Thus, U1 equals max of 0, 1 by 6, minus 1 by 6 equaling 1 by 6, and U2 is the minimum of 1, 5 by 6, 5 by 6 equaling 5 by 6. Since U1 is less than U2, the two endpoints of the clipped line are minus 1 plus 12 into 1 by 6, 7 plus minus 6 into 1 by 6, and minus 1 plus 12 into 5 by 6, 7 plus minus 6 into 5 by 6 equaling 9, 2. Cyrus-Beck parametric line clipping algorithm. This algorithm is more efficient than the Cohen-Sutherland algorithm. It employs parametric line representation and simple dot products. Parametric equation of line P0 P1 is P of t equals P0 plus t into P1 minus P0. Let Ni be the outward normal edge EI. Now pick any arbitrary point PEI on edge EI, then the dot product Ni into Pt minus PEI determines whether the point Pt is inside the clip edge or outside the clip edge or on the clip edge. The point P of t is inside if Ni dot P of t minus PEI is less than 0. The point P of t is outside if Ni dot P of t minus PEI is greater than 0. The point P of t is on the edge if Ni dot P of t minus PEI is equal to 0, intersection point. Now we can solve for the value of t at the intersection of P0 P1 with the edge Ni dot P of t minus P of EI minus PEI equals 0. First substitute for P of t, replacing P of t with P naught plus t into P1 minus P naught. Ni into P naught plus t of P1 minus P0 minus PEI equals 0. Next, group terms and distribute the dot product. Ni into P naught minus PEI plus Ni into t into P1 minus P naught equals 0. Let d equals P1 minus P naught be the vector from P naught to P1 and solve for t. T equals Ni into P naught minus PEI over minus Ni into d. It is valid for the following conditions. Ni not equals 0, error cannot happen. D not equal to 0, P1 is not equal to P0. Ni into d not equal to 0, P naught P1 is not parallel to EI. Example of Cyrus-Beck algorithm. Compute t for each clip rectangle edge. Discard values of t outside. 0, 1. They are not on line segment TR, TB, TR. Classify other candidates more carefully TL. Cyrus-Beck classifying intersections. Potentially entering intersection PE. Ni into D less than 0, angle greater than 90 degrees implies TL. Potentially leaving intersection PL. Ni dot D is greater than 0, angle less than 90 degrees implies TT. Comparison between Liang-Boskie and Cyrus-Beck parametric algorithms is shown in this table. Polygon clipping. A polygon boundary processed with the line clipper may be displayed as a series of unconnected line segments as shown in this figure, depending on the orientation of the polygon to the clipping window. What we really want to display is a bounded area after clipping as shown in this figure. For polygon clipping, we require an algorithm that will generate one or more closed areas that are then scan converted for the appropriate area fill. The output of a polygon clipper should be a sequence of vertices that defines the clipped polygon boundaries. Sutherland Hodgman polygon clipping. We can correctly clip a polygon by processing the polygon boundary as a whole against each window edge. This could be accomplished by processing all polygon vertices against each clip rectangle boundary in turn. Beginning with the initial set of polygon vertices, we could first clip the polygon against the left rectangle boundary to produce a new sequence of vertices. The new set of vertices could then be successively passed to a right boundary clipper, a bottom boundary clipper, and a top boundary clipper as shown in this figure. At each step, a new sequence of output vertices is generated and passed to the next window boundary clipper. There are 4 possible cases when processing vertices in sequence around the perimeter of a polygon. As each pair of adjacent polygon vertices is passed to a window boundary clipper, we make the following tests. If the first vertex is outside the window boundary and the second vertex is inside, both the intersection point of the polygon edge with the window boundary and the second vertex are added to the output vertex list. If both input vertices are inside the window boundary, only the second vertex is added to the output vertex list. If the first vertex inside the window boundary and the second vertex is outside, only the edge intersection with the window boundary is added to the output vertex list. If both the input vertices are outside the window boundary, nothing is added to the output list. These 4 cases are illustrated in this figure for successive pairs of polygon vertices. Once all vertices have been processed for one clip window boundary, the output list of vertices is clipped against the next window boundary. We illustrate this method by processing the area in this figure against the left window boundary. Vertices 1 and 2 are found to be on the outside of the boundary. Moving along to vertex 3, which is inside, we calculate the intersection and save both the intersection point and vertex 3. Vertices 4 and 5 are determined to be inside, and they also are saved. The sixth and final vertex is outside, so we find and save the intersection point. Using the 5 saved points, we would repeat the process for the next window boundary. Implementing the algorithm as we have just described requires setting up storage for an output list of vertices as a polygon is clipped against each window boundary. We can eliminate the intermediate output vertex lists by simply clipping individual vertices at each step and passing the clipped vertices onto the next boundary clipper. This can be done with parallel processes or a single processor and a pipeline of clipping routines. A point, either an input vertex or a calculated intersect point, is added to the output vertex list only after it has been determined to be inside or on a window boundary by all 4 boundary clippers. Otherwise, the point does not continue in the pipeline. This figure shows a polygon and its intersection points with a clip window. In this figure, we illustrate the progression of the polygon vertices through a pipeline of boundary clippers. The following procedure demonstrates the pipeline clipping approach. An array S records the most recent point that was clipped for each clip window boundary. The main routine passes each vertex P to the clip point routine for clipping against the first window boundary. If the line defined by endpoints P and S boundary crosses this window boundary, then the intersection is calculated and passed to the next clipping stage. If P is inside the window, it is passed to the next clipping stage. Any point that survives clipping against all window boundaries is then entered into the output array of points. The array first point stores for each window boundary the first point clipped against that boundary. After all polygon vertices have been processed, a closing routine clips lines defined by the first and last points clipped against each boundary. The Sutherland-Hodgman polygon clipping algorithm is now shown on the screen. Convex polygons are correctly clipped by the Sutherland-Hodgman algorithm, but concave polygons may be displayed with extraneous lines as demonstrated in this figure. This occurs when the clipped polygon should have 2 or more separate sections, but since there is only one output vertex list, the last vertex in the list is always joined to the first vertex. There are several things we could do to correctly display concave polygons. For one, we could split the concave polygon into 2 or more convex polygons and process each convex polygon separately. Another possibility is to modify the Sutherland-Hodgman approach to check the final vertex list for multiple vertex points along any clip window boundary and correctly join pairs of vertices. Finally, we could use a more general polygon clipper such as the Weiler algorithm. Weiler polygon clipping. Here the vertex processing procedures for window boundaries are modified so that the concave polygons are displayed correctly. This clipping procedure was developed as a method for identifying visible surfaces, and so it can be applied with arbitrary polygon clipping regions. The basic idea in this algorithm is that instead always of proceeding around the polygon edges as vertices are processed, we sometimes want to follow the window boundaries. Which path we follow depends on the polygon processing direction, clockwise or counterclockwise, and whether tile pair of polygon vertices currently being processed represents an outside to inside pair or an inside to outside pair. For clockwise processing of polygon vertices, we use the following rules. For an outside to inside pair of vertices, follow the polygon boundary. For an inside to outside pair of vertices, follow the window boundary in a clockwise direction. In this figure, the processing direction in the Weiler algorithm and the resulting clipped polygon is shown for a rectangular clipping window. An improvement on the Weiler algorithm is the Weiler algorithm, which applied constructive solid geometry ideas to clip an arbitrary polygon against any polygon clipping region. This figure illustrates the general idea in this approach. For the two polygons, the correctly clipped polygon is calculated as the intersection of the clipping polygon and the polygon object. Other polygon clipping algorithms. The various parametric line clipping methods have also been adapted to polygon clipping, and they are particularly well suited for clipping against convex polygon clipping windows. The Liang-Boskie line clipper, for example, can be extended to polygon clipping with a general approach similar to that of the Sutherland-Hodgman method. Parametric line representations are used to process polygon edges in order around the polygon perimeter using region testing procedures similar to those used in line clipping. Text clipping. There are several techniques that can be used to provide text clipping in a graphics package. The clipping technique used will depend on the methods used to generate characters and the requirements of a particular application. The simplest method for processing character strings relative to the window boundary is to use the all or none string clipping strategy shown in this figure. Figure shows text clipping using a bounding rectangle about the entire string. If all the string is inside a clip window, we keep it. Otherwise, the string is discarded. This procedure is implemented by considering a boundary rectangle around the text pattern. The boundary positions of the rectangle are then compared to the window boundaries, and the string is rejected if there is any overlap. This method produces the fastest text clipping. An alternative to rejecting an entire character string that overlaps a window boundary is to use the all or none character clipping strategy. Here we discard only those characters that are not completely inside the window. See figure. In this case, the boundary limits of individual characters are compared to the window. Any character that either overlaps or is outside a window boundary is clipped. A final method for handling text clipping is to clip the components of individual characters. We now treat characters in much the same way that we treated lines. When individual character overlaps a clip window boundary, we clip off the parts of the character that are outside the window. See figure. Outline character fonts formed with line segments can be processed in this way using a line clipping algorithm. Characters defined with bitmaps would be clipped by comparing the relative position of the individual pixels in the character grid patterns to the clipping boundaries. Different input modes. Input modes. Functions to provide input can be structured to operate in various input modes, which specify how the program and input devices interact. Input could be initiated by a program, or the program and input devices both could be operating simultaneously, or data input could be initiated by the devices. Three input modes are request mode, sample mode, event mode. Request mode. In request mode, the application program initiates data entry. Input values are requested and processing is suspended until the required values are received. This input mode corresponds to typical input operation in a general programming language. The program and the input devices operate alternately. Devices are put into a wait state until an input request is made. Then the program waits until the data are delivered. Sample mode. In sample mode, the application program and input devices operate independently. Input devices may be operating at the same time that the program is processing other data. New input values from the input devices are stored, replacing previously input data values. When the program requires new data, it samples the current values from the input devices. Event mode. In event mode, the input devices initiate data input to the application program. The program and the input devices again operate concurrently, but now the input devices deliver data to an input queue. All input data are saved. When the program requires new data, it goes to the data queue. Any number of devices can be operating at the same time in sample and event modes. Some can be operating in sample mode while others are operating in event mode. But only one device at a time can be providing input in request mode. An input mode within a logical class for a particular physical device operating on a specified workstation is declared with one of 6 input class functions of the form set mode, ws, device code, input mode, echo flag. Where device code is a positive integer, input mode is assigned to one of the values request, sample or event. And parameter echo flag is assigned either the value of echo or the value no echo. Device code assignment is installation dependent. One possible assignment of device codes is shown in the table. Using the assignments in this table, we could make the following declarations. Set locator mode 1, 2, sample, no echo. Set text mode 2, 1, request echo. Set pick mode 4, 3, event echo. Thus the graphics tablet is declared to be a locator device in a sample mode on workstation 1 with no input data feedback echo. The keyboard is a text device in request mode on workstation 2 with input echo, and the mouse is declared to be a pick device in event mode on workstation 4 with input echo. Request mode. Input commands used in this mode correspond to standard input functions in a high-level programming language. When we ask for an input in request mode, other processing is suspended until the input is received. After a device has been assigned to request mode, input requests can be made to that device using one of the 6 logical class functions represented by the following. Request, ws, device code, status, and so on. Values input with this function are the workstation code and the device code. Returned values are assigned to parameter status and to the data parameters corresponding to the requested logical class. A value of OK or none is returned in parameter status according to the validity of the input data. A value of none indicates that the input device was activated so as to produce invalid data. For locator input, this could mean that the coordinates were out of range. For pick input, the device could have been activated while not pointing at a structure, or break button on the input device could have been pressed. A return value of none can be used as an end of data signal to terminate a programming sequence. Locator and stroke input in request mode. The request functions for these 2 logical input classes are request locator, ws, dev code, status, view index, point. Request stroke, ws, dev code, nmax, status, view index, n, points. For locator input, pt is the world coordinate position selected. For stroke input, pts is a list of n coordinate positions where parameter nmax gives the maximum number of points that can go in the input list. Parameter view index is assigned the 2-dimensional view index number. Determination of a world coordinate position is a two-step process. The physical device selects a point in device coordinates, usually from the video display screen, and the inverse of the workstation transformation is performed to obtain the corresponding point in normalized device coordinates. Then the inverse of the window to viewport mapping is carried out to get to viewing coordinates, then to world coordinates. Since two or more views may overlap on a device, the correct viewing transformation is identified according to the view transformation input priority number. By default, this is the same as the view index number, and the lower the number, the higher the priority. View index 0 has a high priority. We can change the view priority relative to another reference viewing transformation with set view transformation input priority method, where view index identifies the viewing transformation whose priority is to be changed. Ref view index identifies the reference viewing transformation, and parameter priority is assigned either the value lower or the value higher. For example, we can alter the priority of the first four viewing transformations on workstation 1 as shown in this figure with the sequence of functions: set view transformation input priority 1, 3, 1 higher, set view transformation input priority 1, 0, 2 lower. This figure shows rearranging viewing priorities. String input in request mode. Here the request input function is request string ws devcode status nchars string. Parameter string in this function is assigned an input string. The number of characters in the string is given in parameter nchars. Valuator input in request mode. A numerical value is input in request mode with the request valuator ws devcode status value. Parameter value can be assigned any real number value. Choice input in request mode. We make a menu selection with the following request function. Request choice ws devcode status item num. Parameter item num is assigned a positive integer value corresponding to the menu item selected. Pick input in request mode. For this mode, we obtain a structure identifier number with the function request pick ws devcode max path depth status path depth pick path. Parameter pick path is a list of information identifying the primitive selected. This list contains a structure name, pick identifier for the primitive, and the element sequence number. Parameter pick depth is the number of levels returned in pick path, and max path depth is a specified maximum path depth that can be included in pick path. Subparts of a structure can be labeled for pick input with the following function. Set pick identifier, pick ID. An example of sub-labeling during structure creation is given in the following programming sequence. Picking of structures and subparts of structures is also controlled by some workstation filters. Objects cannot be picked if they are invisible. Also, we can set the ability to pick objects independently of their visibility. This is accomplished with the pick filter. Set pick filter ws devcode pickables non-pickables, where the set pickables contains the names of objects, structures and primitives that we may want to select with a specified pick device. Similarly, the set non-pickables contains the names of objects that we do not want to be available for picking with this input device. Sample mode. Once sample mode has been set for one or more physical devices, data input begins without waiting for program direction. If a joystick has been designated as a located device in a sample mode, coordinate values for the current position of the activated joystick are immediately stored. As the activated stick position changes, the stored values are continually replaced with the coordinates of the current stick position. Sampling of the current values from the physical device in this mode begins when a sample command is encountered in the application program. A locator device is sampled with one of the 6 logical class functions represented by the following: sample, WS, device code, and so on. Some device classes have a status parameter in sample mode and some do not. Other input parameters are the same as in request mode. As an example of sample input, suppose we want to translate and rotate a selected object. The final translation position for the object can be obtained with the locator, and the rotation angle can be supplied by a Valuator device, as demonstrated in the following statements. Event mode. When an input device is placed in event mode, the program and device operate simultaneously. Data input from the device is accumulated in an event queue or input queue. All input devices active in event mode can enter data, referred to as events, into this single event queue, with each device entering data values as they are generated. At any one time, the event queue can contain a mixture of data types in the order they were input. Data entered into the queue are identified according to logical class, workstation number, and physical device code. An application program can be directed to check the event queue for any input with the function await event, time, WS, device class, device code. Parameter time is used to set a maximum waiting time for the application program. If the queue happens to be empty, processing is suspended until either the number of seconds specified in time has elapsed or an input arrives. Should the waiting time run out before data values are input, the parameter device class is assigned the value none. When time is given the value 0, the program checks the queue and immediately returns to other processing if the queue is empty. If processing is directed to the event queue with the await event function and the queue is not empty, the first event in the queue is transferred to a current event record. The particular logical device class, such as locator or stroke that made this input, is stored in parameter device class. Codes identifying the particular workstation and physical device that made the input are stored in parameters WS and device code respectively. To retrieve a data input from the current event record, an event mode input function is used. The functions in event mode are similar to those in request and sample modes. However, no workstation and device code parameters are necessary in the commands, since the values for these parameters are stored in the data record. A user retrieves data with get method. For example, to ask for locator input, we invoke the function getLocator viewIndex pt. In the following program section, we give an example of the use of the await event and get functions. A set of points from a tablet, device code 2, on workstation 1 is input to plot a series of straight line segments connecting the input coordinates. The repeat until loop bypasses any data from other devices that might be in the queue. If the tablet is the only active input device in event mode, this loop is not necessary. A number of devices can be used at the same time in event mode for rapid interactive processing of displays. The following statements plot input lines from a tablet with attributes specified by a button box. Some additional housekeeping functions can be used in event mode. Functions for clearing the event queue are useful when a process is terminated and a new application is to begin. These functions can be set to clear the entire queue or to clear only data associated with specified input devices and workstations. Concurrent use of input modes. An example of the simultaneous use of input devices in different modes is given in the following procedure. An object is dragged around the screen with the mouse. When a final position has been selected, a button is pressed to determine any further movement of the object. The mouse positions are obtained in sample mode, and the button input is sent to the event queue. Interactive picture construction techniques. There are several techniques that are incorporated into graphics packages to aid the interactive construction of pictures. Various input options can be provided so that coordinate information entered with locator and stroke devices can be adjusted or interpreted according to a selected option. For example, we can restrict all lines to be either horizontal or vertical. Input coordinates can establish the position or boundaries for objects to be drawn, or they can be used to rearrange previously displayed objects. Basic positioning methods. Coordinate values supplied by a locator input are often used with positioning methods to specify a location for displaying an object or a character string. We interactively select coordinate positions with the pointing device, usually by positioning the screen cursor. Just how the object or text string positioning is performed depends on the selected options. With a text string, for example, the screen point could be taken as a center string position or the start or end position of the string. For lines, straight line segments can be displayed between two selected screen positions. As an aid in positioning objects, numeric values for selected positions can be echoed on the screen. Using the echoed coordinate values as a guide, we can make adjustments to the selected location to obtain accurate positioning. Constraints. With some applications, certain types of prescribed orientations or object alignments are useful. A constraint is a rule for altering input coordinate values to produce a specified orientation or alignment of the displayed coordinates. There are many kinds of constraint functions that can be specified, but the most common constraint is a horizontal or vertical alignment of straight lines. This type of constraint, shown in the following two figures, is useful in forming network layouts. With this constraint, we can create horizontal and vertical lines without worrying about precise specification of endpoint coordinates. A horizontal or vertical constraint is implemented by determining whether any two input coordinate endpoints are more nearly horizontal or more nearly vertical. If the difference in the y values of the two endpoints is smaller than the difference in x values, a horizontal line is displayed. Otherwise, a vertical line is shown. Other kinds of constraints can be applied to input coordinates to produce a variety of alignments. Lines could be constrained to have a particular slant, such as 45 degrees, and input coordinates could be constrained to lie along predefined paths, such as circular arcs. Grids. Another kind of constraint is a grid of rectangular lines displayed in some part of the screen area. When a grid is used, any input coordinate position is rounded to the nearest intersection of two grid lines. This figure illustrates line drawing with a grid. Each of the two cursor positions is shifted to the nearest grid intersection point, and the line is drawn between these grid points. Grids facilitate object constructions because a new line can be joined easily to a previously drawn line by selecting any position near the endpoint grid intersection of one end of the displayed line. Spacing between the grid lines is often an option that can be set by the user. Similarly, grids can be turned on and off, and it is sometimes possible to use partial grids and grids of different sizes in different screen areas. Gravity field. In the construction of figures, we sometimes need to connect lines at positions between endpoints. Since exact positioning of the screen cursor at the connecting point can be difficult, graphics packages can be designed to convert any input position near a line to a position on the line. This conversion of input position is accomplished by creating a gravity field area around the line. Any selected position within the gravity field of a line is moved, gravitated, to the nearest position on the line. A gravity field area around a line is illustrated with a shaded boundary shown in this figure. Areas around the endpoints are enlarged to make it easier for us to connect lines at their endpoints. Selected positions in one of the circular areas of gravity field are attracted to the endpoint in that area. The size of gravity fields is chosen large enough to aid positioning, but small enough to reduce chances of overlap with other lines. If many lines are displayed, gravity areas can overlap and it may be difficult to specify points correctly. Normally, the boundary for the gravity field is not displayed. Rubber band methods. Straight lines can be constructed and positioned using rubber band methods, which stretch out a line from a starting position as the screen cursor is moved. This figure demonstrates the rubber band method. We first select a screen position for one endpoint of the line. Then, as the cursor moves around, the line is displayed from the start position to the current position of the cursor. When we finally select a second screen position, the other line endpoint is set. Rubber band methods are used to construct and position other objects besides straight lines. This figure demonstrates rubber band construction of a rectangle. This figure shows a rubber band circle construction. Dragging. A technique that is often used in interactive picture construction is to move objects into position by dragging them with the screen cursor. We first select an object, then move the cursor in the direction we want the object to move, and the selected object follows the cursor path. Dragging objects to various positions in a scene is useful in applications where we might want to explore different possibilities before selecting a final location. Painting and drawing. Options for sketching, drawing, and painting come in a variety of forms. Straight lines, polygons, and circles can be generated with methods discussed in the previous sections. Curve drawing options can be provided using standard curved shapes, such as circular arcs and splines, or with freehand sketching procedures. Splines are interactively constructed by specifying a set of discrete screen points that give the general shape of the curve. Then the system fits the set of points with a polynomial curve. In freehand drawing, curves are generated by following the path of a stylus on a graphics tablet or the path of the screen cursor on a video monitor. Once a curve is displayed, the designer can alter the curve shape by adjusting the positions of selected points along the curve path. Line widths, line styles, and other attribute options are also commonly found in painting and drawing packages. Various brush styles, brush patterns, color combinations, object shapes, and surface texture patterns are also available on many systems, particularly those designed as artists' workstations. Some paint systems vary the line width and brush strokes according to the pressure of the artist's hand on the stylus. A window and menu system used with a painting package that allows an artist to select variations of a specified object shape, different surface textures, and a variety of lighting conditions for a scene. Logical classification of input devices. The various kinds of input data are summarized in the following 6 logical device classifications used by FIGS and GKS. Locator, a device for specifying coordinate position x, y. Stroke, a device for specifying a series of coordinate positions. String, a device for specifying text input. Valuator, a device for specifying scalar values. Choice, a device for selecting menu options. Pick, a device for selecting picture components. In some packages, a single logical device is used for both locator and stroke operations. Some other mechanisms, such as switch, can then be used to indicate whether one coordinate position or a stream of positions is to be input. Each of the 6 logical input device classifications can be implemented with any of the hardware devices, but some hardware devices are more convenient for certain kinds of data than others. A device that can be pointed at a screen position is more convenient for entering the coordinate data than a keyboard, for example. Locator devices. A standard method for interactive selection of a coordinate point is by positioning the screen cursor. We can do this with a mouse, joystick, trackball, spaceball, thumb wheels, dials, a digitized stylus, or a hand cursor, or some other cursor positioning device. When the screen cursor is at the desired location, a button is activated to store the coordinates of that screen point. Keyboards can be used for locator input in several ways. A general-purpose keyboard usually has 4 cursor control keys that move the screen cursor up, down, left and right. With an additional 4 keys, we can move the cursor diagonally as well. Rapid cursor movement is accomplished by holding down the selected cursor key. Alternatively, a joystick, joydisk, trackball, or thumb wheels can be mounted on the keyboard for relative cursor movement. As a last resort, we could actually type in coordinate values, but this is a slow process that also requires us to know exact coordinate values. Light pens have also been used to input coordinate positions, but some special implementation considerations are necessary. Since light pens operate by directing light emitted from the screen phosphors, some non-zero intensity level must be present at the coordinate position to be selected. With the raster system, we can paint a color background onto the screen. As long as no black areas are present, a light pen can be used to select any screen position. When it is not possible to eliminate all black areas in a display, such as on a vector system, for example, a light pen can be used as a locator by creating a small light pattern for the pen to detect. The pattern is moved around the screen until it finds the light pen. Stroke device. This class of logical devices is used to input a sequence of coordinate positions. Stroke device input is equivalent to multiple calls to a locator device. The set of input points is often used to display line sections. Many of the physical devices used for generating locator input can be used as stroke devices. Continuous movement of a mouse, trackball, joystick, or tablet hand cursor is translated into a series of input coordinate values. The graphics tablet is one of the more common stroke devices. Button activation can be used to place the tablet into continuous mode. As the cursor is moved across the tablet surface, a stream of coordinate values is generated. This process is used in paintbrush systems that allow artists to draw scenes on the screen and in engineering systems where layouts can be traced and digitized for storage. String devices. The primary physical device used for string input is a keyboard. Input character strings are typically used for picture or graph labels. Other physical devices can be used for generating character patterns in a text writing mode. For this input, individual characters are drawn on the screen with a stroke or locator type device. A pattern recognition program then interprets the characters using a stored dictionary of predefined patterns. Valuator devices. This logical class of devices is employed in graphics systems to input scalar values. Valuators are used for setting various graphics parameters such as rotation angle and scale factors, and for setting physical parameters associated with a particular application, temperature settings, voltage levels, stress factors, etc. A typical physical device is used to provide valuator input in a set of control dials. Floating point numbers within any predefined range are input by rotating the dials. Dial rotations in one direction increases the numeric input value, and opposite rotations decrease a numeric value. Rotary potentiometers convert dial rotation into a corresponding voltage. This voltage is then translated into a real number within a defined scalar range, such as -10.5 to 25.5. Instead of dials, slide potentiometers are sometimes used to convert linear movements into scalar values. Any keyboard with a set of numeric keys can be used as a valuator device. A user simply types the numbers directly in floating point format, although this is a slower method than using dials or slide potentiometers. Joysticks, trackballs, tablets, and other interactive devices can be adapted for valuator input by interpreting pressure or movement of the device relative to the scalar range. For one direction of movement, say left to right, increasing scalar values can be input. Movement in the opposite direction decreases the scalar input value. Another technique for providing valuator input is to display sliders, buttons, rotating scales, and menus on the video monitor. This figure illustrates some possibilities for scale representations. Locator input from a mouse, joystick, spaceball or other device is used to select a coordinate position on the display, and the screen coordinate position is then converted to a numeric input value. As a feedback mechanism for the user, the selected position on scale can be marked with some symbol. Numeric values may also be echoed somewhere on the screen to confirm the selections. Choice devices. Graphics packages use menus to select programming options, parameter values, and object shapes to be used in constructing a picture. See figure. A choice device is defined as one that enters a selection from a list menu of alternatives. Commonly used choice devices are a set of buttons, a cursor positioning device such as a mouse, trackball, or keyboard cursor keys, and a touch panel. A function keyboard or button box designed as a standalone unit is often used to enter menu selections. Usually, each button is programmable so that its function can be altered to suit different applications. Single-purpose buttons have fixed, predefined functions. Programmable function keys and fixed function buttons are often included with other standard keys on a keyboard. For screen selection of listed menu options, we can use cursor control devices. When a coordinate position x, y is selected, it is compared to the coordinate extents of each listed menu item. A menu item with vertical and horizontal boundaries at the coordinate values xmin, xmax, ymin, and ymax is selected if the input coordinates x, y satisfy the inequalities. X lies between xmin and xmax, y lies between ymin and ymax. For larger menus with a few options displayed at a time, a touch panel is commonly used. As with a cursor control device, such as a mouse, a selected screen position is compared to the area occupied by each menu choice. Alternate methods for choice input include keyboard and voice entry. A standard keyboard can be used to type in commands or menu options. For this method of choice input, some abbreviated format is useful. Menu listings can be numbered or given short identifying names. Similar codings can be used with voice input systems. Voice input is particularly useful when the number of options is small, 20 or less. Pick devices. Graphical object selection is a function of this logical class of devices. Pick devices are used to select parts of a scene that are to be transformed or edited in some way. Typical devices used for object selection are the same as those for menu selection, the cursor positioning devices. With a mouse or joystick, we can position the cursor over the primitives in a displayed structure and press the selection button. The position of the cursor is then recorded, and several levels of search may be necessary to locate the particular object, if any, that is to be selected. First, the cursor position is compared to the coordinate extents of the various structures in the scene. If the bounding rectangle of a structure contains the cursor coordinates, the picked structure has been identified. But if two or more structure areas contain the cursor coordinates, further checks are necessary. The coordinate extents of individual lines in each structure can be checked next. If the cursor coordinates are determined to be inside the coordinate extents of only one line, for example, we have identified the picked object. Otherwise, we need additional checks to determine the closest line to the cursor position. One way to find the closest line to the cursor position is to calculate the distances squared from the cursor coordinates x, y to each line segment whose bounding rectangle contains the cursor position. See figure. For a line with endpoints x1, y1 and x2, y2, distance squared from x, y to the line is calculated as d squared equals delta x into y minus y1 minus delta y into x minus x1 the whole squared over delta x squared plus delta y squared, where delta x equals x2 minus x1 and delta y equals y2 minus y1. Various approximations can be used to speed up this distance calculation, or other identification schemes can be used. Another method for finding the closest line to the cursor position is to specify the size of a pick window. The cursor coordinates are centered on this window, and the candidate lines are clipped to the window as shown in this figure. By making the pick window small enough, we can ensure that a single line will cross the window. A method for avoiding the calculation of pick distances or window clipping intersections is to highlight the candidate structures and allow the user to resolve the pick ambiguity. One way to do this is to highlight the structures that overlap the cursor position one by one. The user then signals when the desired structure is highlighted. An alternative to cursor positioning is to use button input to highlight successive structures. A second button is used to stop the process when the desired structures is highlighted. If very many structures are to be searched in this way, the process can be speeded up and an additional button is used to help identify the structure. The first button can initiate a rapid successive highlighting of structures. A second button can again be used to stop the process, and a third button can be used to back up more slowly if the desired structure passed before the operator pressed the stop button. Finally, we could use the keyboard to type in structure names. This is a straightforward but less interactive pick selection method. Descriptive names can be used to help the user in the pick process, but the method has several drawbacks. It is generally slower than interactive picking on the screen, and a user will probably need prompts to remember the various structure names. In addition, picking structure subparts from the keyboard can be more difficult than picking the subparts on the screen. Three-dimensional geometric transformations. Methods for geometric transformations and object modeling in 3 dimensions are extended from 2-dimensional methods by including considerations for the z-coordinate. We now translate an object by specifying a 3-dimensional translation vector, which determines how much the object is to be moved in each of the 3 coordinate directions. Similarly, we scale an object with 3 coordinate scaling factors. The extension for 3-dimensional rotation is less straightforward. When we discussed 2-dimensional rotations in the xy plane, we needed to consider only rotations about the axes that were perpendicular to the xy plane. In 3-dimensional space, we can now select any spatial orientation for the rotation axis. Most graphics packages handle 3-dimensional rotation as a composite of 3 rotations, one for each of the 3 Cartesian axes. Alternatively, a user can easily set up a general rotation matrix given the orientation of the axis and the required rotation angle. As in the 2-dimensional case, we express geometric transformations in matrix form. Any sequence of transformations is then represented as a single matrix formed by concatenating the matrices for the individual transformations in the sequence. Translation. In a 3-dimensional homogeneous coordinate representation, a point is translated, see this figure, from position P equals x, y, z to position P dash equals x dash, y dash, z dash with the matrix operation as follows. Or P dash equals T into P. Parameters Tx, Ty and Tz specifying translation distances for the coordinate directions x, y and z are assigned any real values. The matrix representation is equivalent to the 3 equations x dash equals x plus tx, y dash equals y plus ty, and z dash equals z plus tz. An object is translated in 3 dimensions by transforming each of the defining points of the object. For an object represented as a set of polygon surfaces, we translate each vertex of each surface, see figure, and redraw the polygon facets in the new position. We obtain the inverse of the translation matrix by negating the translation distances Tx, Ty, and Tz. This produces a translation in the opposite direction, and the product of a translation matrix and its inverse produces the identity matrix. Rotation. To generate a rotation transformation for an object, we must designate an axis of rotation, about which the object is to be rotated, and the amount of angular rotation. Unlike two-dimensional applications, where all transformations are carried out in the xy plane, a three-dimensional rotation can be specified around any line in space. The easiest rotation axes to handle are those that are parallel to the coordinate axes. Also, we can use combinations of coordinate axis rotations, along with appropriate translations, to specify any general rotation. By convention, positive rotation angles produce counterclockwise rotations about a coordinate axis if we are looking along the positive half of the axis towards the coordinate origin, as shown in the figure, where positive rotations in the xy plane are counterclockwise about axis parallel to the z-axis. Coordinate axis rotations. The two-dimensional z-axis rotation equations are easily extended to three dimensions. X dash equals x cos theta minus y sin theta, y dash equals x sin theta plus y cos theta, z dash equals z. Parameter theta specifies the rotation angle. In homogeneous coordinate form, the three-dimensional z-axis rotation equations are expressed as shown below, which we can write more compactly as p dash equals rz theta into p. This figure illustrates rotation of an object about the z-axis. Transformation equations for rotations about the other two coordinate axes can be obtained with a cyclic permutation of the coordinate parameters x, y, and z. That is, we use the replacements x leading to y, to z, to x, as illustrated in this figure. This figure shows a cyclic permutation of the Cartesian coordinate axes to produce the three sets of coordinate axis rotation equations. We get the equations for an x-axis rotation. Y dash equals y cos theta minus z sin theta, z dash equals y sin theta plus z cos theta, x dash equals x, which can be written in the homogeneous coordinate form as shown, or p dash equals rx of theta into p. Rotation of an object around the x-axis is demonstrated in this figure. Cyclically permuting coordinates gives us a transformation equations for y-axis rotation. Z dash equals z cos theta minus x sin theta, x dash equals z sin theta plus x cos theta, y dash equals y. The matrix representations for y-axis rotation is shown in the figure, or p dash equals ry theta into p. An example of y-axis rotation is shown in the figure. An inverse rotation matrix is formed by replacing the rotation angle theta by minus theta. Negative values for rotation angles generate rotations in a clockwise direction, so the identity matrix is produced when any rotation matrix is multiplied by its inverse. Since only the sign function is affected by the change in sign of the rotation angles, the inverse matrix can also be obtained by interchanging rows and columns. That is, we can calculate the inverse of any rotation matrix R by evaluating its transpose. R inverse equals R transpose. This method for obtaining an inverse matrix holds also for any composite rotation matrix. General three-dimensional rotations. A rotation matrix for any axis that does not coincide with the coordinate axis can be set up as a composite transformation involving combinations of translations and the coordinate axis rotations. We obtain the required composite matrix by first setting up the transformation sequence that moves the selected rotation axis onto one of the coordinate axes. Then we set up the rotation matrix about that coordinate axis for the specified rotation angle. The last step is to obtain the inverse transformation sequence that returns the rotation axis to its original position. In the special case where an object is to be rotated about an axis that is parallel to one of the coordinate axes, we can attain the desired rotation with the following transformation sequence. Translate the object so that the rotation axis coincides with the parallel coordinate axis. Perform the specified rotation about that axis. translate the object so that the rotation axis is moved back to its original position. The steps in this sequence are illustrated in the figure. Any coordinate position P on the object in this figure is transformed with the sequence shown as P' equals T inverse into R x theta into T into P, where the composite matrix for the transformation is R theta is equal to T inverse into Rx theta into T, which is of the same form as the two-dimensional transformation sequence for rotation about an arbitrary pivot point. When an object is to be rotated about an axis that is not parallel to one of the coordinate axes, we need to perform some additional transformations. In this case also, we need rotations to align the axis with the selected coordinate axis and to bring the axis back to its original orientation. Given the specifications for the rotation axis and the rotation angle, we can accomplish the required rotation in 5 steps. 1. Translate the object so that the rotation axis passes through the coordinate origin. 2. Rotate the object so that the axis of rotation coincides with one of the coordinate axes. 3. Perform the specified rotation about that coordinate axis. 4. Apply inverse rotations to bring the rotation axis back to its original orientation. 5. Apply the inverse translation to bring the rotation axis back to its original position. We can transform the rotation axis onto any one of the 3 coordinate axes. The z-axis is a reasonable choice, and the following discussion shows how to set up the transformation matrices for getting the rotation axis onto the z-axis and returning the rotation axis to its original position. See figure. A rotation axis can be defined with 2 coordinate positions, as in this figure, or with 1 coordinate point and direction angles, or direction cosines, between the rotation axis and the 2 of the coordinate axes. Figure shows an axis of rotation, dashed line, defined with points P1 and P2. The direction for the unit axis vector u is determined by the specified rotation direction. We will assume that the rotation axis is defined by 2 points as illustrated, and that the direction of rotation is to be counterclockwise when looking along the axis from P2 to P1. An axis vector is then defined by the 2 points as V equals P2 minus P1 equals x2 minus x1, y2 minus y1, z2 minus z1. A unit vector u is then defined along the rotation axis as u equals V over modulus V equals A, B, C, where the components A, B, and C of the unit vector u are the direction cosines for the rotation axis. A equals x2 minus x1 over mod V, B equals y2 minus y1 over mod V, and C equals z2 minus z1 over mod V. If the rotation is to be in the opposite direction, clockwise when viewing from P2 to P1, then we would reverse axis vector V and unit vector u so that they point from P2 to P1. The first step in the transformation sequence for the desired rotation is to set up the translation matrix that repositions the rotation axis so that it passes through the coordinate origin. For the desired direction of rotation, in previous figure, we accomplished this by moving point P1 to the origin. If the rotation direction had been specified in the opposite direction, we would move P2 to the origin. The translation matrix is as shown below, which repositions the rotation axis and the object as shown in this figure. Translation of the rotation axis to the coordinate origin. Now we need the transformations that will put the rotation axis on the z-axis. We can use the coordinate axis rotations to accomplish this alignment in 2 steps. There are a number of ways to perform the 2 steps. We will first rotate about the x-axis to transform vector u into the xz plane. Then we swing u around to the z-axis using a y-axis rotation. These 2 rotations are illustrated in this figure for one possible orientation of vector u. Unit vector u is rotated about the x-axis to bring it into the xz plane, and then it is rotated around the y-axis to align it with the z-axis. Since rotation calculations involve sine and cosine functions, we can use standard vector operations to obtain elements of the two rotation matrices. Dot product operations allow us to determine the cosine terms, and vector cross products provide a means for obtaining the sine terms. We establish the transformation matrix for rotation around the z-axis by determining the values for the sine and cosine of the rotation angle necessary to get the u in the xz plane. This rotation angle is the angle between the projection of u in the yz plane and the positive z-axis. See figure. Figure shows rotation of u around the x-axis into the xz plane, which is accomplished by rotating u dash, the projection of u in the yz plane, through angle alpha onto the z-axis. If we designate the projection of u in the yz plane as the vector u dash equals 0, b, c, then the cosine of the rotation angle alpha can be determined from the dot product of u dash and the unit vector u along the z-axis. Cos alpha equals u dash into uz over modulus of u dash and uz equals c over d. D equals square root of b squared plus c squared. Similarly, we can determine the sine of alpha from the cross product of u dash and uz. The coordinate independent form of this cross product is u dash into uz equals ux into modulus of u dash modulus of uz sine alpha. And the Cartesian form for the cross product gives us u dash cross uz equals ux and b. Equating the right sides of equations as given above and noting that uz modulus of uz equals 1 and modulus of u dash equals d, we have d sine alpha equals b. Sine alpha equals b by d. Now that we have determined the values for cos alpha and sine alpha in terms of the components of vector u, we can set up the matrix for rotation of u about the x-axis, as shown. This matrix rotates unit vector u about the x-axis into the xz plane. Next, we need to determine the form of the transformation matrix that will swing the unit vector in the xz plane counterclockwise around the y-axis onto the positive z-axis. The orientation of the unit vector in the xz plane after rotation about the x-axis is shown in this figure. Figure shows rotation of unit vector u double dash vector u after rotation into the xz plane about the y-axis. Positive rotation angle beta aligns u double dash with vector uz. This vector labeled u double dash has the value a for its x component, since rotation above the x-axis leaves the x component unchanged. Its z component is d, the magnitude of u dash, because vector u dash has been rotated onto the z-axis, and the y component of u double dash is 0, because it now lies in the xz plane. Again, we can determine the cosine of rotation angle beta from expressions for the dot product of unit vectors u double dash and uz. Cos beta equals u double dash and uz over modulus of u double dash modulus of uz equals d. Since modulus of uz equals modulus of u double dash equals 1. Comparing the coordinate independent form of the cross product, u double dash cross uz equals uy into modulus of u double dash modulus of uz sine beta. With the Cartesian form, u double dash cross uz equals uy and minus a. We find that sine beta equals minus a. Thus, the transformation matrix for rotation of u double dash about the y-axis is as shown below. With transformation matrices, we have aligned the rotation axis with the positive z-axis. The specified rotation angle theta can now be applied as a rotation about the z-axis, rz of theta as shown. To complete the required rotation about the given axis, we need to transform the rotation axis back to its original position. The transformation matrix for rotation about an arbitrary axis that can be expressed as the composition of these 7 individual transformations, as shown. A somewhat quicker but perhaps less intuitive method for obtaining the composite rotation matrix Ry, beta, and Rx, alpha is to take advantage of the form of the composite matrix for any sequence of three-dimensional rotations as shown. The upper left 3 by 3 submatrix of this matrix is orthogonal. This means that the rows or the columns of this submatrix form a set of orthogonal unit vectors that are rotated by matrix R onto the x, y, and z axis respectively, as shown here. Therefore, we can consider a local coordinate system defined by the rotation axis and simply form a matrix whose columns are the local unit coordinate vectors. Assuming that the rotation axis is not parallel to any coordinate axis, we can form the following local set of unit vectors. uz dash equals u, uy dash equals u cross ux over modulus of u cross ux, ux dash equals uy dash cross uz dash. This is shown in this figure. The figure shows the local coordinate system for a rotation axis defined by unit vector u. If we express the elements of the local unit vectors for the rotation axis as u dash x equals ux dash 1, u dash x2, u dash x3, u dash y equals u dash y1, u dash y2, u dash y3, u dash z equals u dash z, u dash z1, u dash z2, u dash z3. Then the required composite matrix equal to the product Ry of beta and Rx of alpha is as shown below. This matrix transforms the unit vectors ux dash, uy dash, and uz dash onto the x, y, and z axis respectively. Thus the rotation axis is aligned with the z axis since uz dash equals rotations with quaternions. A more efficient method for obtaining rotation about a specified axis is to use a quaternion representation for the rotation transformation. Quaternions are useful also in a number of other computer graphic procedures, including three-dimensional rotation calculations. They require less storage space than 4x4 matrices, and it is simpler to write quaternion procedures for transformation sequences. This is particularly important in animations that require complicated motion sequences and motion interpolations between two given positions of an object. Scaling. The matrix expression for the scaling transformation of a position P equals x, y, z relative to the coordinate origin can be written as shown, or P dash equals S into P, where scaling parameters Sx, xy, and sz are assigned any positive values. Explicit expressions for the coordinate transformations for scaling relative to the origin are x dash equals x into sx, y dash equals y into sy, and z dash equals z into sz. Scaling an object with transformation is change the size of the object and reposition the object relative to the coordinate origin. Also, if the transformation parameters are not all equal, relative dimensions in the object are changed. We preserve the original shape of an object with the uniform scaling Sx equals Sy equals Sz. The result of scaling an object uniformly with each scaling parameter set to 2, that is, doubling the size of an object, is shown in this figure. Scaling with respect to a selected fixed position xf, yf, zf can be represented with the following transformation sequence. 1. Translate the fixed point to the origin. 2. Scale the object relative to the coordinate origin. 3. Translate the fixed point back to its original position. This sequence of transformations is demonstrated in this figure. Figure shows that scaling an object relative to a selected fixed point is equivalent to the sequence of transformations shown. The matrix representation for an arbitrary fixed point scaling can then be expressed as a concatenation of these translate-scale-translate transformations as We form the inverse scaling matrix by replacing the scaling parameters Sx, Xy, and Sz with their reciprocals. The inverse matrix generates an opposite scaling transformation, so the concatenation of any scaling matrix and its inverse produces the identity matrix. Other transformations. In addition to translation, rotation, and scaling, there are various additional transformations that are often useful in three-dimensional graphics applications. Two of these are reflection and shear. Reflections. A three-dimensional reflection can be performed relative to the selected reflection axis or with respect to a selected reflection plane. In general, three-dimensional reflection matrices are set up similarly to those for 2 dimensions. Reflections relative to a given axis are equivalent to 180 degrees rotations about that axis. Reflections with respect to a plane are equivalent to 180 degrees rotations in 4-dimensional space. When the reflection plane is a coordinate plane, either xy, xz, or yz, we can think of the transformation as a conversion between left-handed and right-handed systems. An example of a reflection that coordinates specification from a right-handed system to a left-handed system or vice versa is shown in the figure. This transformation changes the sign of the z coordinates, leaving the x and y coordinate values unchanged. The matrix representation for this reflection of points relative to the xy plane is as shown below. Transformation matrices for inverting x and y values are defined similarly as reflections relative to the yz plane and xz plane respectively. Reflections about other planes can be obtained as a combination of rotations and coordinate plane reflections. Shears. Shearing transformations can be used to modify object shapes. They are also useful in three-dimensional viewing for obtaining general projection transformations. In 2 dimensions, we discuss transformations relative to x or y axes to produce distortions in the shape of objects. In 3 dimensions, we can also generate shears relative to the z-axis. As an example of 3-dimensional shearing, the following transformation produces a z-axis shear. Parameters a and b can be assigned any real values. The effect of this transformation matrix is to alter x and y coordinate values by an amount that is proportional to the z value while leaving the z coordinate unchanged. Boundaries of planes that are perpendicular to the z-axis are thus shifted by an amount proportional to z. An example of the effect of this shearing matrix on a unit cube is shown in the figure for shearing values a equals b equals 1. Shearing matrices for the x-axis and y-axis are defined similarly. Composite transformations. As with 2-dimensional transformations, we form a composite 3-dimensional transformation by multiplying the matrix representations for the individual operations in the transformation sequence. This concatenation is carried out from right to left, where the rightmost matrix is the first transformation be applied to an object and the leftmost matrix is the last transformation. A sequence of basic 3-dimensional geometric transformations are combined to produce a single composite transformation, which is then applied to the coordinate definition of an object. Solved problems. Problem. Define tilting as a rotation about the x-axis, followed by a rotation about the y-axis. A. Find the tilting matrix. B. Does the order of performing the rotational matter? Solution. We can find the required transformation T by concatenating 2 rotation matrices. This is not the same matrix as in part A, thus the order of rotation matters. Problem. Find a transformation AV which aligns a given vector V with the vector K along the positive z-axis. Solution. Refer the figure. Let V be equal to AI plus BJ plus CK. We perform the alignment through the following sequence of transformations. Step 1. Rotate about the x-axis by an angle θ1 so that V rotates into the upper half of the xz plane as a vector V1. Step 2. Rotate the vector v1 about the y-axis by an angle minus theta 2 so that vi rotates to the positive z-axis as the vector v2. Implementing step 1, we observe that the required angle of rotation theta 1 can be found by looking at the projection of v onto the yz plane. We assume that b and c are not both 0. From triangle OP-B, sin theta 1 equals b over square root of b squared plus c squared, and cos theta 1 equals c over square root of b squared plus c squared. The required rotation is applying the rotation to the vector v produces a vector v1 with the components a, 0, square root of b squared plus c squared. Implementing step 2, we see that the rotation of theta 2 degrees is required, and so from triangle OQQ', sin minus theta 2 equals minus sin theta 2 equals minus a over square root of a squared plus b squared plus c squared. And then, since mod of v equals square root of a squared plus b squared plus c squared, and the introducing the notation lambda equals b squared plus c squared square root of b squared plus c squared, we find if both b and c are 0, then v equals ai, and so lambda equals 0. In this case, only a plus or minus 90 degrees rotation about the y-axis is required. So if lambda equals 0, it follows that. In the same manner, we calculate the inverse transformation that aligns the vector k with the vector v. Problem: let an axis of rotation L be specified by a direction vector v and location point P. Find the transformation for rotation theta naught about L. Refer the given figure. Solution: we can find the required transformation by the following steps. Translate P to the origin. Align V with the vector k. Rotate by theta naught about k. Reverse steps 2 and 1. So, here AV is the transformation described in previous problem. Two-dimensional geometric transformations. The basic geometric transformations are translation, rotation, and scaling. Other transformations that are often applied to objects include reflection and shear. Basic transformations. Here we first discuss general procedures for applying translation, rotation, and scaling parameters to reposition and resize two-dimensional objects. Later, we will discuss about how transformation equations can be expressed in a more convenient matrix formulation that allows efficient combination of object transformations. Translation. A translation is applied to an object by repositioning it along a straight line path from one coordinate location to another. We translate a two-dimensional point by adding translation distances tx and ty to the original coordinate position x, y to move the point to a new position x dash, y dash. The figure shows translating a point from position P to position P dash with translation vector t. The translation distance pair tx, ty is called a translation vector or shift vector. We can express the translation equations as follows. We can express these equations as a single matrix equation by using column vectors to represent the coordinate positions and the translation vector as shown on the screen. This allows us to write the two-dimensional translation equations in the matrix form. P dash equals P plus T. Sometimes matrix transformation equations are expressed in terms of coordinate row vectors instead of column vectors. In this case, we would write the matrix representations as P equals xy and T equals tx, ty. Since the column vector representation for a point is standard mathematical notation, and since many graphics packages, for example, GKS, and PHIGS also use a column vector representation. Translation is a rigid body transformation that moves objects without deformation. That is, every point on the object is translated by the same amount. A straight line segment is translated by applying the transformation equation P' equals P plus T to each of the line endpoints and redrawing the line between the new endpoint positions. Polygons are translated by adding the translation vector to the coordinate position of each vertex and regenerating the polygon using the new set of vertex coordinates and the current attribute settings. This figure illustrates the application of a specified translation vector to move an object from one position to another. Similar methods are used to translate curved objects. To change the position of a circle or ellipse, we translate the center coordinates and redraw the figure in the new location. We translate other curves, for example splines, by displacing the coordinate positions defining the objects. Then we reconstruct the curved paths using the translated coordinate positions. Rotation. A two-dimensional rotation is applied to an object by repositioning it along a circular path in the XY plane. To generate a rotation, we specify a rotation angle theta and the position x, r, y, r of the rotation point or pivot point about which the object is to be rotated, as shown in this figure. Positive values for the rotation angle define counterclockwise rotations about the pivot point, and negative values rotate the objects in the clockwise direction. This transformation can also be described as a rotation about a rotation axis that is perpendicular to the xy plane and passes through the pivot point. We first determine the transformation equations for rotation of a point position P when the pivot point is at the coordinate origin. The angular and coordinate relationships of the original and transformed point positions are shown in this figure. In this figure, r is the constant distance of the point from the origin, angle phi is the original angular position of the point from the horizontal, and theta is the rotation angle. Using standard trigonometric identities, we can express the transformed coordinates in terms of angles theta and phi as shown below. The original coordinates of the point in polar coordinates are x equals r cos phi, y equals r sin phi. We obtain the transformation equations for rotating a point at position x, y through an angle theta about the origin. X dash equals x cos theta minus y sin theta, y dash equals x sin theta plus y cos theta. We can write the rotation equations in the matrix form. P dash equals R and P, where the rotation matrix is as shown on the screen. When coordinate positions are represented as row vectors instead of column vectors, the matrix product in rotation equation is transposed so that the transformed row coordinate vector x dash y dash is calculated as P dash transpose equals R and P transpose equals P transpose and R transpose, where P transpose x, y and the transpose R transpose of matrix R is obtained by interchanging rows and columns. For a rotation matrix, the transpose is obtained by simply changing the sign of the sign terms. Rotation of a point about an arbitrary pivot point is illustrated in this figure. Figure shows rotating a point from position x, y to position x dash, y dash through an angle theta about a rotation point xr, yr. Using the trigonometric relationships in this figure, we can generalize the transformation equation to obtain the transformation equations for rotation of a point about any specified rotation position xr, yr as shown below. Thus, the matrix expression modified to include pivot coordinates by matrix addition of a column vector, whose elements contain the additive translation terms. As with translations, rotations are rigid body transformations that move objects without deformation. Every point on an object is rotated through the same angle. A straight line segment is rotated by applying the rotation equations to each of the line endpoints and redrawing the line between the new endpoint positions. Polygons are rotated by displacing each vertex through the specified rotation angle and regenerating the polygon using the new vertices. Curved lines are rotated by repositioning the defining points and redrawing the curves. A circle or an ellipse, for instance, can be rotated about a non-central axis by moving the center position through the arc that subtends the specified rotation angle. An ellipse can be rotated about its center coordinates by rotating the major and minor axes. Solved example. Problem. Perform a 45-degree rotation of triangle A 0, 0, B 1, 1, C 5, 2 about the origin. Solution. We represent the triangle by a matrix formed from the homogeneous coordinates of the vertices as shown, and the matrix of rotation is as seen on the screen. So the coordinates A-B-C- of the rotated triangle ABC can be found as thus A' equals 0, 0, B' equals 0, square root 2 and C' equals 3 square root 2 divided by 2, 7 square root 2 divided by 2. Problem. Define tilting as a rotation about the x-axis followed by a rotation about the y-axis. A. Find the tilting matrix, and B. Does the order of performing the rotation matter? Solution. A. We can find the required transformation T by concatenating two matrices. T equals R theta x, I and R theta y, j. B. We multiply R theta x, j and R theta y, I to obtain the below matrix. This is not the same matrix as in part A, thus the order of rotation matters. Scaling. A scaling transformation alters the size of an object. This operation can be carried out for polygons by multiplying the coordinate values x, y of each vertex by scaling factors sx and sy to produce the transformed coordinates x', y', as shown. Scaling factor sx scales objects in the x direction and scaling factor sy scales objects in the y direction. The above transformation equations can also be written in the matrix form as shown on screen, where S is the 2 by 2 scaling matrix, or P' equals S and P. Any positive numeric values can be assigned to the scaling factors Sx and Sy. Values less than 1 reduce the size of objects. Values greater than 1 produce an enlargement. Specifying a value of 1 for both Sx and Sy leaves the size of objects unchanged. When Sx and Sy are assigned the same value, a uniform scaling is produced that maintains relative object proportions. Unequal values for Sx and Xy result in a differential scaling that is often used in design applications where pictures are constructed from a few basic shapes that can be adjusted by scaling and positioning transformations as shown in this figure. This figure shows turning a square into a rectangle with scaling factors Sx equals 2 and Sy equals 1. Objects transformed are both scaled and repositioned. Scaling factors with values less than 1 move objects closer to the coordinate origin, while values greater than 1 move coordinate positions farther from the origin. This figure illustrates scaling a line by assigning the value 0.5 to both Sx and Sy. Both the line length and the distance from the origin are reduced by a factor of 1 by 2. This figure shows a line scaled using Sx minus Sy equals 0.5 is reduced in size and moved closer to the coordinate origin. We can control the location of a scaled object by choosing a position called the fixed point, that is to remain unchanged after the scaling transformation. Coordinates for the fixed point xf, yf can be chosen as one of the vertices, the object centroid, or any other position as shown in this figure. This figure shows a scaling relative to a chosen fixed point xf, yf. A polygon is then scaled relative to the fixed point by scaling the distance from each vertex to the fixed point. Objects transformed are both scaled and with coordinates x, y. Scaling factors with values less than 1, y dash move object closer to the coordinate origin, while values greater than 1 rewrite these scaling transformations to separate from the multiplicative and additive terms. This figure illustrates scaling a line by assigning the value 0.5 to both xf and sy, 1 minus sx. Y dash both the line length and the distance from the origin plus are reduced by a factor of 1 by 2, where the additive terms xf of 1 minus sx and yf of 1 minus sy are constant for all points in the object. Including coordinates for a fixed point in the scaling equations is similar to including coordinates for a pivot point in the rotation equations. We can set up a column vector whose elements are the constant terms in the above scaling transform equation. Then we add this column vector to the product S and P. In the next section, we discuss a matrix formulation for the transformation equations that involve only matrix multiplication. Polygons are scaled by applying transformations to each vertex and then regenerating the polygon using the transformed vertices. Other objects are scaled by applying the scaling transformation equations to the parameters defining the objects. An ellipse in standard position is resized by scaling the semi-major and semi-minor axes and redrawing the ellipse about the designated center coordinates. Uniform scaling of a circle is done by simply adjusting the radius. Then we redisplay the circle about the center coordinates using the transformed radius. Solved examples. Problem: an object is defined with respect to a coordinate system whose units are measured in feet. If an observer's coordinate system uses inches as the basic unit, what is the coordinate transformation used to describe the object coordinates in the observer's coordinate system? Solution: since there are 12 inches to a feet, the required transformation can be described by a coordinate scaling transformation with S equals 1 by 12 or as shown on screen. And so, this yields the following result. Problem: find the equation of the circle x dash squared plus y dash squared equals 1 in terms of xy coordinates, assuming that the x dash y dash coordinate system from a scaling of a units in the x direction and b units in the y direction. Solution: from the equations for a coordinate scaling transformations, we find x dash equals 1 by a x, y dash equals 1 by b y. Substituting, we have the following equation. Notice that as a result of scaling, the equation of the circle is transformed to the equation of an ellipse in the xy coordinate system. Matrix representations and homogeneous coordinates. Many graphics applications involve sequences of geometric transformations. An animation, for example, might require an object to be translated and rotated at each increment of the motion. In design and picture construction applications, we perform translations, rotations, and scalings to fit the picture components in their proper positions. Each of the basic transformations can be expressed in the general matrix form, with coordinate positions P and P' represented as column vectors. P' equals M1 and P plus M2. Matrix M1 is a 2 by 2 array containing multiplicative factors, and M2 is a 2-element column matrix containing translational terms. For translation, M1 is the identity matrix. For rotation or scaling, M2 contains the translational terms associated with the pivot point or scaling fixed point. To produce a sequence of transformations with these equations, such as scaling followed by rotation then a translation, we must calculate the transformed coordinates one step at a time. First, coordinate positions are scaled, then these scaled coordinates are rotated, and finally the rotated coordinates are translated. A more efficient approach would be to combine the transformations so that the final coordinate positions are obtained directly from the initial coordinates, thereby eliminating the calculation of intermediate coordinate values. To be able to do this, we need to reformulate the above equation of the basic transformations to eliminate the matrix addition associated with the translation terms in M2. We can combine the multiplicative and translation terms for two-dimensional geometric transformations into a single matrix representation by expanding the 2 by 2 matrix representations to 3 by 3 matrices. This allows us to express all transformation equations as matrix multiplications, providing that we also expand the matrix representations for coordinate positions. To express any two-dimensional transformation as a matrix multiplication, we represent each Cartesian coordinate position x, y with the homogeneous coordinate triple xh, yh, h, where x equals xh over h and y equals yh over h. Thus, a general homogeneous coordinate representation can also be written as h dot x, h dot y, h. For two-dimensional geometric transformations, we can choose the homogeneous parameter h to be any non-zero value. Thus, there is an infinite number of equivalent homogeneous representations for each coordinate point x, y. A convenient choice is simply to set h equal 1. Each two-dimensional position is then represented with homogeneous coordinates x, y, 1. Other values for parameter h are needed, for example, in matrix formulations of three-dimensional viewing transformations. The term homogeneous coordinates is used in mathematics to refer to the effect of this representation on Cartesian equations. When a Cartesian point x, y is converted to a homogeneous representation xh, yh, h, equations containing x and y, such as f of x, y equals 0, become homogeneous equations in the three parameters xh, yh, and h. This just means that if each of the three parameters is replaced by any value v times that parameter, the value v can be factored out of the equations. Expressing positions in homogeneous coordinates allows us to represent all geometric transformation equations as matrix multiplications. Coordinates are represented with 3-element column vectors, and transformation operations are written as 3 by 3 matrices. For translation, we have the following matrix, which we can write in the abbreviated form with T of Tx, Ty as a 3 by 3 translation matrix. P dash equals T of Tx, Ty into P. The inverse of the translation matrix is obtained by replacing the translation parameters Tx and Ty with their negatives minus Tx and minus Ty. Similarly, rotation transformation equations about the coordinate origin are now written as follows, or as P dash equals r theta into P. The rotation transformation operator r theta is a 3 by 3 matrix in the rotation transformation equations with rotation parameter theta. We get the inverse rotation matrix when theta is replaced with negative theta. Finally, a scaling transformation relative to the coordinate origin is now expressed as a matrix multiplication shown, or P dash equals S of Sx, Sy and P, where S of Xx and Sy is a 3 by 3 matrix with parameters Sx and Sy. Replacing these parameters with their multiplicative inverses of 1 by Sx and 1 by Sy yields the inverse scaling matrix. Matrix representations are standard methods for implementing transformations in graphic systems. In many systems, rotation and scaling functions produce transformations with respect to the coordinate origin. Rotations and scalings relative to other reference positions are then handled as a succession of transformation operations. An alternate approach in graphics package is to provide parameters in the transformation functions for the scaling fixed point coordinates and the pivot point coordinates. General rotation and scaling matrices that include the pivot or fixed point are then set up directly without the need to invoke a succession of transformation functions. Composite transformations. We can set up a matrix for any sequence of transformations as a composite transformation matrix by calculating the matrix product of the individual transformations. Forming products of transformation matrices is often referred to as concatenation or composition of matrices. For column matrix representation of coordinate positions, we form composite transformations by multiplying matrices in order from right to left. That is, each successive transformation matrix pre-multiplies the product of the preceding transformation matrices. Translations. If two successive translation vectors tx1, ty1 and tx2, ty2 are applied to a coordinate position P, the final transformation location P' is calculated as shown on screen, where P and P' are represented as homogeneous coordinate column vectors. We can verify this result by calculating the matrix product for the two associative groupings. Also, the composite transformation matrix for this sequence of translations is as shown here. Or it can be stated as T of tx2, ty2 and T of tx1, ty1 equals T of tx1 plus tx2, ty1 plus ty2, which demonstrates that two successive translations are additive. Rotations. Two successive rotations applied to point P produce a transformed position. P' equals r theta 2 multiplied by r theta 1 and P equals r theta 2 and r theta 1 multiplied by P. By multiplying the two rotation matrices, we can verify that the two successive rotations are additive. R theta 2 and r theta 1 equals r of theta 1 plus theta 2. So that the final rotated coordinates can be calculated with the composite rotation matrix as P' equals r of theta 1 plus theta 2 and P. Concatenating transformation matrices for two successive scaling operations produces the following composite scaling matrix. Or it can also be stated as S of Sx2, Sy2 and S of Sx1, Sy1 equals S of Sx1 and Sx2, Sy1 and Sy2. The resulting matrix in this case indicates that the successive scaling operations are multiplicative. That is, if we were to triple the size of an object twice in succession, the final size would be 9 times that of the original. General pivot point rotation. With a graphics package that only provides a rotate function for revolving objects about the coordinate origin, we can generate rotations about any selected pivot point xr, yr by performing the following sequence translate, rotate, translate operations. Translate the object so that the pivot point position is moved to the coordinate origin. Rotate the object about the coordinate origin. Translate the object so that the pivot point is returned to its original position. This transformation sequence is illustrated in the following figure. This figure shows a transformation sequence for rotating an object about a specified pivot point using the rotation matrix. The composite transformation matrix for this sequence is obtained with the concatenation as shown on screen, which can also be expressed in the form T of xr, yr and r theta and T of minus xr, minus yr equals r of xr, yr, theta, where T of minus xr minus yr equals T inverse of xr, yr. In general, a rotate function can be set up to accept parameters for pivot point coordinates as well as the rotation angle and to generate automatically the rotation matrix. General fixed point scaling. This figure illustrates a transformation sequence to produce scaling with respect to a selected fixed position, xf, yf, using a scaling function that can only scale relative to the coordinate origin. The figure shows a transformation sequence for scaling an object with respect to a specified fixed position using the scaling matrix S of xx, sy. Translate the object so that the fixed point coincides with the coordinate origin. Scale the object with respect to the coordinate origin. Use the inverse translation of step 1 to return the object to its original position. Concatenating the matrices for these three operations produces the required scaling matrix as shown on screen. Or it can also be stated as T of xf, yf and S of sx, sy and T of minus xf minus yf equals S of xf, yf, sx, sy. This transformation is automatically generated on systems that provide a scale function that accepts coordinates for the fixed point. General scaling directions. Parameters sx and sy scale objects along the x and y directions. We can scale an object in other directions by rotating the object to align the desired scaling directions with the coordinate axes before applying the scaling transformation. Suppose we want to apply scaling factors with values specified by parameters S1 and S2 in the directions shown in this figure. Scaling parameters S1 and S2 are to be applied in orthogonal directions defined by the angular displacement theta. To accomplish the scaling without changing the orientation of the object, we first perform a rotation so that the directions for S1 and S2 coincide with the x and y axes respectively. Then the scaling transformation is applied, followed by an opposite rotation to return points to their original orientations. The composite matrix resulting from the product of these three transformations is as shown on the screen. As an example of this scaling transformation, we turn a unit square into a parallelogram as shown in this figure by stretching it along diagonal from 0, 0 to 1, 1. This figure shows a square converted to a parallelogram using the composite transformation matrix. We rotate the diagonal onto the y-axis and double its length with the transformation parameters theta equaling 45 degrees and S1 equals 1 and S2 equals 2. We assume that scaling was to be performed relative to the origin. We could take this scaling operation one step further and concatenate the matrix with translation operators, so that the composite matrix would include parameters for the specification of a scaling fixed position. Concatenation properties. Matrix multiplication is associative. For any three matrices A, B and C, the matrix product A and B and C can be performed by first multiplying A and B or by first multiplying B and C. A and B and C equals A and B and C equals A and B and C. Therefore, we can evaluate matrix products using either a left to right or a right to left associative grouping. On the other hand, transformation products may not be commutative. The matrix product A and B is not equal to B, and A in general. This means that if you want to translate and rotate an object, you must be careful about the order in which the composite matrix is evaluated in the figure. Reversing the order in which a sequence of transformations is performed may affect the transformed positions of an object. In A, an object is first translated then rotated. In B, the object is rotated first and then translated. For some special cases such as a sequence of transformations all of the same kind, the multiplication of transformation matrices is commutative. As an example, two successive rotations could be performed in either order and the final position would be the same. This commutative property holds also for two successive translations or two successive scalings. Another commutative pair of operations is rotation and uniform scaling, Sx equals Sy. General composite transformations and computational efficiency. A general two-dimensional transformation representing a combination of transactions, rotations, and scalings can be expressed as shown on the screen. The four elements RSIJ are the multiplicative rotation scaling terms in the transformation that involve only rotation angles and scaling factors. Elements TRSX and TRSY are the translational terms containing combinations of translation distances, pivot point and fixed point coordinates, and rotation angles and scaling parameters. For example, if an object is to be scaled and rotated about its centroid coordinates x, y, and then translated, the values for the elements of the composite transformation matrix are as expressed on the screen. Although general two-dimensional transformation matrix equation requires 9 multiplications and 6 additions, the explicit calculations for the transformed coordinates are x dash equals x and rs xx plus y and rs xy plus trsx dash. Y dash equals y and rs yx plus y and rx yy plus trsy. Thus, we actually only need to perform 4 multiplications and 4 additions to transform coordinate positions. This is the maximum number of computations required for any transformation sequence once the individual matrices have been concatenated and the elements of the composite matrix evaluated. Without concatenation, the individual transformations would be applied one at a time and the number of calculations could be significantly increased. An efficient implementation for the transformation operations, therefore, is to formulate transformation matrices, concatenate any transformation sequence, and calculate transformed coordinates. On parallel systems, direct matrix multiplications with the composite transformation matrix can be equally efficient. A general rigid body transformation matrix involving only translations and rotations can be expressed in the form as shown on screen, where the 4 elements Rij are the multiplicative rotation terms and the elements Trx and Try are the translational terms. A rigid body change in coordinate position is also sometimes referred to as rigid motion transformations. All angles and distances between coordinate positions are unchanged by the transformation. The rigid body transformation matrix has the property that its upper left 2 by 2 submatrix is an orthogonal matrix. This means that if we consider each row of the submatrix as a vector, then the two vectors Rxx, Rxy and Ryx, Ryy form an orthogonal set of unit vectors. Each vector has unit length. Rxx squared plus Rxy squared equals Ryx squared plus Ryy squared equals 1. And the vectors are perpendicular. Their dot product is 0. Rxx Ryx plus Rxy Ryy equals 0. Therefore, if these unit vectors are transformed by the rotation submatrix Rxx, Rxy is converted to a unit vector along the x-axis, and Ryx, Ryy is transformed into a unit vector along the y-axis of the coordinate system, as shown below. As an example, the following rigid body transformation first rotates an object through an angle theta about a pivot point xr, yr and then translates as shown. Here the orthogonal unit vectors in the upper left 2 by 2 submatrix are cos theta and minus sin theta, and sin theta, cos theta, and as shown below. Unit vector sin theta, cos theta is converted by the transformation matrix to the unit vector 0, 1 in the y direction. The orthogonal property of rotation matrices is useful for constructing a rotation matrix when we know the final orientation of an object rather than the amount of angular rotation necessary to put the object into that position. Directions for the desired orientation of an object could be determined by the alignment of a certain object in a scene or by selected positions in the scene. This figure shows an object that is to be aligned with the unit direction vectors u' and v'. In this figure, the rotation matrix for revolving an object from position A to position B can be constructed with the values of the unit orientation vectors u' and v' relative to the original orientation. Assuming that the original object orientation, as shown in part A, is aligned with the coordinate axis, we construct the desired transformation by assigning the elements of u' to the first row of the rotation matrix and the elements of v' to the second row. This can be a convenient method for obtaining the transformation matrix for rotation within a local or object coordinate system when we know the final orientation vectors. A similar transformation is a conversion of object descriptions from one coordinate system to another. Since rotation calculations require trigonometric evaluations and several multiplications for each transformed point, computational efficiency can become an important consideration in rotation transformations. In animations and other applications that involve many repeated transformations and small rotation angles, we can use approximations and iterative calculations to reduce computations in the composite transformation equations. When the rotation angle is small, the trigonometric function can be replaced with approximation values based on the first few terms of their power series expansions. For small enough angles less than 10 degrees, cos theta is approximately 1 and sin theta has a value very close to the value of theta in radians. If we are rotating in small angular steps about the origin, for instance, we can set cos theta to be 1 and reduce transformation calculations at each step to 2 multiplications and 2 additions for each set of coordinates to be rotated. X' equals x minus y sin theta, y' equals x sin theta plus y, where sin theta is evaluated once for all steps, assuming that the rotation angle does not change. The error introduced by this approximation at each step decreases as the rotation angle decreases. But even with small rotation angles, the accumulated error over many steps can become quite large. We can control the accumulated error by estimating the error in x' and y' at each step and resetting object positions when the error accumulation becomes too great. Composite transformations often involve inverse matrix calculations. Transformation sequences for general scaling directions and for reflections and shears, for example, can be described with inverse rotation components. The inverse matrix representations for the basic geometric transformations can be generated with simple procedures. An inverse translation matrix is obtained by changing the signs of the translation distances, and an inverse rotation matrix is obtained by performing a matrix transpose or changing the sign of the sign terms. These operations are much simpler than direct inverse matrix calculations. An implementation of composite transformations is given in the following procedure. Matrix M is initialized to the identity matrix. As each individual transformation is specified, it is concatenated with the total transformation matrix M. When all transformations have been specified, this composite transformation is applied to a given object. For this example, a polygon is scaled and rotated about a given reference point. Then the object is translated. This figure shows the original and final positions of the polygon transformed by this sequence, as shown below. Other transformations. Basic transformations such as translation, rotation, and scaling are included in most graphics packages. Some packages provide a few additional transformations that are useful in certain applications. Two such transformations are reflection and shear. Reflection. A reflection is a transformation that produces a mirror image of an object. The mirror image for a two-dimensional reflection is generated relative to an axis of reflection by rotating the object 180 degrees about the reflection axis. We can choose an axis of reflection in the xy plane or perpendicular to the xy plane. When the reflection axis is a line in the xy plane, the rotation path about this axis is in a plane perpendicular to the xy plane. For reflection axes that are perpendicular to the xy plane, the rotation path is in the xy plane. Following are examples of some common reflections. Reflection about the line y equals 0, the x-axis is accomplished with the transformation matrix, as shown on screen. This transformation keeps x values the same, but flips the y values of coordinate positions. The resulting orientation of an object after it has been reflected about the x-axis is shown in this figure. This figure shows the reflection of an object about the x-axis. To envision the rotation transformation path for this reflection, we can think of the flat object moving out of the xy plane and rotating 180 degrees through three-dimensional space about the x-axis and back into the xy plane on the other side of the x-axis. A reflection about the y-axis flips x-coordinates while keeping y-coordinates the same. The matrix for this transformation is as shown on the screen. This figure illustrates the change in position of an object that has been reflected about the line x equals 0. This figure shows a reflection of an object about the y-axis. The equivalent rotation in this case is 180 degrees through three-dimensional space about the y-axis. We flip both the x and y coordinates of a point by reflecting relative to an axis that is perpendicular to the xy plane and that passes through the coordinate origin. This transformation, referred to as a reflection relative to the coordinate origin, has the matrix representation shown on the screen. An example of reflection about the origin is shown in this figure. The figure shows the reflection of an object relative to an axis perpendicular to the xy plane and passing through the coordinate origin. The reflection matrix is the rotation matrix r theta, with theta being 180 degrees. We are simply rotating the object in the xy plane half a revolution about the origin. Reflection can be generalized to any reflection point in the xy plane as shown in this figure. This figure shows a reflection of an object relative to an axis perpendicular to the xy plane and passing through the point P RFL. This reflection is the same as a 180-degree rotation in the xy plane using the reflection point as the pivot point. If we choose the reflection axis as the diagonal line y equals x as shown in this figure, reflection of an object with respect to the line y equals x, the reflection matrix is shown here. We can derive this matrix by concatenating a sequence of rotation and coordinate axis reflection matrices. One possible sequence is shown in these figures. A. Clockwise rotation of 45 degrees. B. Reflection about the x-axis. C. Counterclockwise rotation by 45 degrees. Here we first perform a clockwise rotation through a 45-degree angle which rotates the line y equals x onto the x-axis. Next we perform a reflection with respect to the x-axis. The final step is to rotate the line y equals x back to its original position with a counterclockwise rotation through 45 degrees. An equivalent sequence of transformations is first to reflect the object about the x-axis and then to rotate counterclockwise 90 degrees. To obtain a transformation matrix for reflection about the diagonal y equals minus x, we could concatenate matrices for the transformation sequence. Clockwise rotation by 45 degrees, reflection about the y-axis, and counterclockwise rotation by 45 degrees. The resulting transformation matrix will be as shown on the screen. This figure shows the original and final positions for an object transformed with this reflection matrix, as shown below. Reflection with respect to the line y equals minus x. Reflections about any line y equals mx plus b in the xy plane can be accomplished with the combination of translate, rotate, reflect transformations. In general, we first translate the line so that it passes through the origin. Then we can rotate the line onto one of the coordinate axes and reflect about that axis. Finally, we restore the line to its original position with the inverse rotation and translation transformations. We can implement reflections with respect to the coordinate axes or coordinate origin as scaling transformations with negative scaling factors. Also, elements of the reflection matrix can be set to values other than plus or minus 1. Values whose magnitudes are greater than 1 shift the mirror image farther from the reflection axis, and values with magnitudes less than 1 bring the mirror image closer to the reflection axis. Shear. A transformation that distorts the shape of an object such that the transformed shape appears as if the object were composed of internal layers that had been caused to slide over each other is called a shear. Two common shearing transformations are those that shift coordinate w values and those that shift y values. An x-direction shear relative to the x-axis is produced with the transformation matrix, which is shown, which transform the coordinate positions as x dash equals x plus shx and y dash equals y. Any real number can be assigned to the shear parameter shx. A coordinate position x, y is then shifted horizontally by an amount proportional to its distance y value from the x-axis, y equals 0. Setting shx to 2, for example, changes the square in this figure into a parallelogram. Negative values for shx shift the coordinate positions to the left. This figure shows a unit square A is converted to a parallelogram B using the x-direction shear matrix with shx equals 2. We can generate the x-direction shears relative to the other reference lines with the matrix as shown below. The coordinate positions are now transformed as x dash equals x plus shx, y minus y ref, y dash equals y. An example of this shearing transformation is given in this figure for a shear parameter value of 1 by 2 relative to the line y ref equals minus 1. This figure shows a unit square A is transformed to a shifted parallelogram B with shx equals 1 by 2 and y ref equals minus 1 in the shear matrix. A y-direction shear relative to the line x equals x ref is generated with the transformation matrix as shown below. This generates the transformed coordinate positions as x dash equals x, y dash equals s, h, y, x minus x ref plus y. This transformation shifts a coordinate position vertically by an amount proportional to its distance from the reference line x equals x ref. This figure illustrates the conversion of a square into a parallelogram with shy equals 1 by 2 and x ref equals minus 1. This figure shows a unit square A is turning into a shifted parallelogram B with parameter values shy equals 1 by 2 and x ref equals minus 1 in the y direction. Shearing operations can be expressed as sequences of basic transformations. The x-direction shear matrix, for example, can be written as a composite transformation involving a series of rotation and scaling matrices that would scale the unit square along its diagonal, while maintaining the original lengths and orientations of edges parallel to the x-axis. Shifts in the positions of objects relative to the shearing reference lines are equivalent to translations. Transformations between coordinate systems. Graphics applications often require the transformation of object descriptions from one coordinate system to another. Sometimes objects are described in non-Cartesian reference frames that take advantage of object symmetries. Coordinate descriptions in these systems must then be converted to Cartesian device coordinates for display. Some examples of two-dimensional non-Cartesian systems are polar coordinates, elliptical coordinates, and parabolic coordinates. In other cases, we need to transform between two Cartesian systems. For modeling and design applications, individual objects may be defined in their own local Cartesian references, and the local coordinates must then be transformed to position the objects within the overall scene coordinate system. A facility management program for office layouts, for instance, has individual coordinate reference descriptions for chairs and tables and other furniture that can be placed into a floor plan with multiple copies of the chairs and other items in different positions. In other applications, we may simply want to reorient the coordinate reference for displaying a scene. Here we consider transformations between two Cartesian frames of reference. This figure shows two Cartesian systems with the coordinate origins at 0, 0 and x0, y0 and with an orientation angle theta between the x and the x dash axes. This figure shows a Cartesian x-y system positioned at x0, y0 with orientation theta in an xy Cartesian system. To transform object descriptions from xy coordinates to the x-y axis onto the xy axis. This is done in two steps. Translate so that the origin x0, y0 of the x-y system is moved to the origin of the xy system. Rotate the x-axis onto the x-axis. Translation of the coordinate origin is expressed with a matrix operation, as shown below. And the orientation of the two systems after the translation operation would appear as in this figure that follows. Position of the reference frames after translating the origin of the x-y system to the coordinate origin of the xy system is shown in this figure. To get the axes of the two systems into coincidence, we then perform the clockwise rotation, which is represented in this matrix. Concatenating these two transformations matrices gives us the complete composite matrix for transforming object descriptions from the xy system to the x-y system. mxy, x-y equals r of minus theta and t of minus x0, minus y0. An alternate method for getting the orientation of the second coordinate system is to specify a vector v that indicates a direction for the positive y dash axis as shown in this figure. This figure shows the Cartesian system x-y with origin as p0 equals x0, y0 and the y dash axis parallel to the vector v. Vector v is specified as a point in the xy reference frame relative to the origin of the xy system. A unit vector in the y dash direction can then be obtained as shown below. And we obtain the unit vector u along the x dash axis by rotating v 90 degrees clockwise, shown below. The matrix to rotate the x-y system into coincidence with xy system can be written as shown. As an example, suppose we choose the orientation for the y dash axis as v equals -1, 0. Then the x dash axis is in the positive y direction and the rotation transformation matrix will be as shown. In an interactive application, it may be more convenient to choose a direction for v relative to position p0 than it is to specify it relative to the xy coordinate origin. Unit vectors u and v would then be oriented as shown in this figure. A Cartesian x-y system defined with two coordinate positions p0 and p1 within an xy reference frame. The components of v are now calculated as v equals p1 minus p0 over modulus of p1 minus p0. And u is obtained as the perpendicular to v that forms a right-handed Cartesian system. Solved problems. Show the magnification of an object while keeping its center fixed. Let the geometric center be located at C, h, k. Choosing a magnification factor of s greater than 1, we construct the transformation by performing the following sequence of basic transformations. Step 1. Translate the object so that its center coincides with the origin as shown in the figure. Step 2. Scale the object with respect to the origin as shown here. Step 3. Translate the scaled object back to the original position as in this graph. Express as a composite transformation matrix, that is CTM, the transformation which magnifies an object about its center, C, h, k, from the previous example. The required transformation SSC can be written as SSC equals TV minus 1, SSS TV equals the matrix shown below. Conclusion. In this chapter, we have covered the following in detail: two-dimensional geometric transformations, clipping, point clipping, line clipping, polygon clipping, text clipping, logical classification of input devices, different input modes, interactive picture construction techniques, three-dimensional geometric transformations.